Welcome, fellow dreamer. You have found a place of calm and rest. This evening, we're going to explore a quiet revolution that began with a fortunate accident in a London laboratory, where a simple mold would unlock one of medicine's greatest treasures. We'll journey through the remarkable story of penicillin, from its unexpected discovery to the extraordinary efforts that brought it to the world when it was needed most. Accompanied by soothing music and abstract imagery, we'll be uncovering little-known wonders and fascinating stories that gently feed your curiosity as you drift toward sleep. If you enjoy these calm adventures with us, don't be shy. Like, subscribe, and leave a comment to help other smart sleepers dream too. And now, take a deep breath, let your body sink into comfort, and allow your mind to rest and your eyes to close as the tale unfolds before you. In the early decades of the 20th century, a simple scratch in the garden could become a death sentence. A sore throat might develop into a condition that no physician could cure. Childhood itself was a precarious journey through countless invisible dangers, and even the most skilled doctors could do little more than watch and wait when infection took hold. This was the world before antibiotics, a time when the human body's own defenses stood as the primary barrier between illness and recovery. Medicine had made remarkable advances in understanding disease, in surgical techniques, and in public health measures. Yet when bacteria invaded the bloodstream or infected a wound, physicians remained largely powerless. They could clean, they could comfort, they could provide supportive care, but they could not directly attack the microscopic invaders that were slowly overwhelming their patients. Consider the experience of a young mother in the 1920s, developing a fever a few days after childbirth. What began as slight discomfort could rapidly progress to a raging infection known as puerperal fever or childbed fever. Doctors understood by this time that bacteria caused the condition, transferred perhaps on unwashed hands or unsterilized instruments. They knew the enemy existed, could even see it under a microscope, but possessed no weapon to fight it once it established itself in the bloodstream. The mother might receive careful nursing, cold compresses for the fever, perhaps some pain relief, but her survival depended almost entirely on whether her own immune system could overcome the infection. Many did not survive. Childbirth, the most natural of human experiences, carried with it a shadow of dread that extended beyond the physical challenges of delivery itself. In hospitals, surgeons faced a cruel irony. The same advancing surgical skills that allowed them to repair injuries and remove diseased organs also created new opportunities for deadly infections. A perfectly executed operation could still result in death days or weeks later when bacteria colonized the surgical site. Post-operative infection was so common that surgeons factored it into their calculations when deciding whether to operate at all. Some conditions that were technically operable were deemed too risky because the likelihood of fatal infection outweighed the potential benefit. The scalpel could cut with precision, but it also created doorways through which invisible enemies could enter. Children faced particular vulnerability in this pre-antibiotic world. Ear infections, which today receive a simple prescription and resolve within days, could spread to the mastoid bone behind the ear, requiring painful surgery to drain the infection. Even with surgery, some children developed meningitis when the infection spread further. Scarlet fever, caused by streptococcal bacteria, could progress from a rash and sore throat to rheumatic fever, permanently damaging heart valves and leaving children as cardiac invalids for their shortened lives. Pneumonia, the infection that fills the lungs with fluid, was called the captain of the men of death for the speed and certainty with which it could claim victims of any age. The everyday dangers seem almost unimaginable from our modern perspective. A blister from new shoes that became infected could require hospitalization. A tooth abscess might spread to the jaw and face, causing grotesque swelling and potentially fatal blood poisoning. Even minor surgery like a tonsillectomy carried significant risk, not from the procedure itself, but from the possibility that bacteria would find their way into the surgical site and begin their destructive work. Physicians of this era were not ignorant or careless. Many were brilliant diagnosticians who could identify diseases with remarkable accuracy. Medical schools taught anatomy, physiology, and pathology with increasing sophistication. Doctors could often tell patients exactly what was wrong with them, which bacteria was causing their infection, and what the likely progression would be. This knowledge, however, brought its own burden. Understanding the cause of suffering, without possessing the means to cure it, created a particular kind of medical helplessness. Some treatments existed, though their effectiveness was limited. Antiseptics could clean wounds and prevent some infections from starting, a crucial advance that had made surgery far safer than in previous centuries. Vaccines protected against certain bacterial diseases like diphtheria. For syphilis, a bacterial infection with devastating long-term effects, arsenic-based compounds offered treatment, though these were toxic and dangerous in their own right. These represented important tools, but they addressed specific situations rather than providing a broad solution to bacterial infection. The absence of effective treatment shaped not just medical practice, but society itself. Families were larger partly because parents expected to lose children to infection. Life insurance companies calculated their premiums, knowing that previously healthy individuals could die suddenly from infections that struck without warning. Hospitals maintained large infectious disease wards where patients were isolated, nursed and monitored, with recovery depending more on chance and constitution than medical intervention. Yet even in this challenging landscape, hope persisted. Scientists around the world were investigating the microscopic realm, learning more each year about bacteria and how they functioned. Some researchers had noticed intriguing phenomena, mysterious instances where bacterial growth was inhibited by unexpected substances. The idea that nature itself might provide weapons against bacteria had begun to emerge in various laboratories, though no one had yet found a practical and safe way to harness this potential. As the 1920s progressed, the medical community accepted bacterial infections as a fundamental limitation of their practice, a problem that resisted solution despite decades of investigation. Doctors learned to work within these constraints, celebrating victories where they occurred and accepting losses as inevitable. Patients and families understood that some illnesses simply had to run their course and that the outcome remained uncertain until the fever broke or the condition worsened beyond recovery. In this world of limited options and sobering realities, few could have imagined that the answer was already taking shape in the natural world around them, in the same molds that spoiled bread and grew in damp corners. The solution to one of medicine's greatest challenges would emerge not from systematic searching, but from careful observation of an accident, from the prepared mind of a researcher who noticed something unusual and chose to investigate rather than simply discard a contaminated laboratory dish. But that discovery still lay ahead, waiting for the right circumstances and the right observer to bring it into focus. The world of the infinitely small remained hidden from human eyes for most of our history. We walked through invisible clouds of life, utterly unaware that entire universes existed in a single drop of water, on our skin, in the very air we breathed. The idea that creatures too small to see could exist at all, let alone cause illness, would have seemed like pure fantasy to most people for thousands of years. The key to unlocking this invisible realm required an invention that would extend human vision beyond its natural limits. In the late 16th century, spectacle makers in the Netherlands began experimenting with combinations of lenses, grinding glass into curved shapes that could magnify small objects. These early optical instruments were crude by modern standards, but they represented humanity's first step toward perceiving what had always been there, just beyond the threshold of visibility. Antony van Leeuwenhoek, a Dutch draper with no formal scientific training, became one of the most important pioneers in revealing this hidden world. In the 1670s, working from his shop in Delft, he crafted tiny lenses with remarkable skill, achieving magnifications far superior to most microscopes of his era. His curiosity knew no bounds. He examined everything he could think of through his lenses: rainwater collected from his roof, scrapings from between his teeth, samples of his own blood. What Leeuwenhoek saw astonished him. In drop after drop of water, he observed tiny creatures swimming about, moving with apparent purpose, living their brief lives completely invisible to the naked eye. He called them animalcules, little animals, and described them in detailed letters to the Royal Society in London. His correspondents found his claims almost impossible to believe, living things so small that hundreds could fit on the head of a pin. It challenged everything people thought they knew about the nature of life itself. The Royal Society members were skeptical until they examined samples with their own microscopes and confirmed his observations. Here was an entirely new realm of existence, teeming with life forms that had never been catalogued or named. Van Leeuwenhoek continued his observations for decades, describing bacteria, protozoa, and other microorganisms with painstaking attention to detail. He was seeing what no human had ever seen before, documenting the shapes and movements of organisms that outnumbered all visible life on Earth. Yet seeing these tiny creatures was one thing. Understanding what they did, how they lived, and whether they had any connection to human health was quite another challenge altogether. For nearly 2 centuries after Leeuwenhoek's discoveries, the nature and significance of microorganisms remained deeply mysterious. Scientists observed them, classified them, marveled at them, but the idea that these minuscule beings could cause disease in creatures millions of times their size seemed implausible to many learned minds. The dominant theory of disease for much of this period centered on miasmas, noxious vapors thought to arise from rotting organic matter. When disease struck, people looked to bad air, foul odors, and environmental conditions as the culprits. The tiny organisms visible under microscopes were considered interesting curiosities, perhaps even products of disease, rather than its cause. The conceptual leap required to see bacteria as active agents of illness took generations to achieve. In the mid-19th century, several researchers began to suspect that microorganisms might play a more active role in fermentation, decay, and perhaps disease. Louis Pasteur in France conducted elegant experiments that demonstrated microorganisms caused fermentation and spoilage. He showed that life did not spontaneously generate from non-living matter as many believed, but that microorganisms came from other microorganisms. His work helped establish that these invisible creatures were real, reproducing biological entities with specific effects on their environment. Pasteur's investigations into diseases of silkworms, beer and wine revealed that specific microorganisms caused specific problems. This specificity was crucial. It suggested that if a particular microbe caused a particular disease, then understanding and controlling that microbe might prevent or cure the disease. The implications were profound, though the full picture would take years to emerge. In Germany, Robert Koch developed rigorous methods for proving that specific bacteria caused specific diseases. Working with anthrax, tuberculosis, and cholera, Koch established a systematic approach to identifying disease-causing organisms. He learned to grow bacteria in pure cultures outside the body, to stain them so they became visible under microscopes, and to demonstrate conclusively that a particular organism was responsible for a particular illness. His postulates, the criteria for establishing a causal relationship between a microbe and a disease, gave researchers a framework for investigating the microbial world's role in human suffering. These discoveries transformed medicine's understanding of illness. Disease was not primarily caused by bad air, or moral failings, or imbalanced humors, as earlier theories had suggested. Many of humanity's most devastating illnesses were caused by living organisms so small that millions could fit in a teaspoon. These organisms entered the body, multiplied, and through their presence and activity, caused the symptoms of disease. The realization was both enlightening and sobering. On one hand, understanding the true cause of bacterial infections opened the possibility of finding treatments or preventive measures. On the other hand, it revealed just how surrounded humans were by potential threats. Bacteria existed everywhere, in water, in food, in soil, on surfaces, on our own bodies. Most were harmless or even beneficial, but some possessed the capacity to cause terrible suffering. As the 19th century drew to a close, medical science had identified many of the bacterial culprits behind common diseases. Physicians could look through microscopes and see the spiral shapes of syphilis bacteria, the rod-shaped forms of tuberculosis, the spherical clusters of Staphylococcus that caused wound infections. They could watch these organisms multiply in laboratory cultures, could study their characteristics and behaviors, but seeing the enemy and fighting the enemy were vastly different challenges. Knowing that bacteria caused disease did not by itself provide a way to stop them. Once they had established an infection inside a living patient, the invisible world had been revealed, its inhabitants identified and catalogued, their destructive capabilities documented. The next challenge was finding a way to kill these organisms without killing the patient who harbored them, a puzzle that would occupy some of the most creative minds in medicine. In the decades following the discovery that bacteria could cause disease, a curious phenomenon began to capture the attention of observant scientists working in their laboratories. They noticed something peculiar, something that seemed almost too convenient to be true. In certain circumstances, bacteria simply stopped growing. Sometimes they even died. And the cause of this bacterial demise was not heat, not chemicals deliberately introduced, but the presence of other living organisms. The idea that one microorganism might harm another was not entirely new. In nature, competition for resources is universal, and the microscopic world proved no exception to this rule. But the notion that this natural antagonism might be harnessed to fight human disease, that was a concept that required both careful observation and imaginative thinking. One of the earliest researchers to document this phenomenon was a French military doctor named Ernest Duchenne. In the year 1896, while still a medical student in Lyon, Duchenne made observations that would prove remarkably prescient, though tragically unrecognized during his lifetime. He noticed that Arab stable boys at the military hospital where he worked had a peculiar practice. They would store their saddles in dark, damp rooms, allowing mold to grow on them. When Duchenne inquired about this seemingly unsanitary habit, the stable boys explained that the moldy saddles actually helped heal saddle sores on the horses. Intrigued by this folk remedy, Duchenne decided to investigate scientifically. He prepared cultures of Penicillium glaucum, a common mold, and combined them with disease-causing bacteria. Then he injected these mixtures into guinea pigs. The results were striking. Animals that received both the mold and the deadly bacteria survived, while those receiving bacteria alone succumbed to infection. Duchenne had in essence demonstrated the antibacterial properties of Penicillium mold more than 3 decades before Fleming's famous discovery. He wrote up his findings in his doctoral thesis, submitted in 1897, and even sent his work to the prestigious Pasteur Institute in Paris. But the young doctor's research went unnoticed. Perhaps it was too far ahead of its time, or perhaps the scientific establishment was not ready to take seriously the observations of an unknown medical student from the provinces. Duchenne himself returned to military service, his research abandoned. He died in 1912 at the age of just 37, never knowing that his early work had pointed toward one of medicine's greatest revolutions. While Duchenne's observations slipped into obscurity, other scientists were approaching similar territory from different directions. In the laboratories of Europe, researchers were beginning to use a new term for what they were observing. They called it antibiosis, from the Greek words meaning against life. It described the phenomenon whereby one organism produced substances that inhibited or killed other organisms. A German scientist named Rudolf Emmerich, working with his colleague Oskar Loew in the 1890s, extracted substances from bacteria that could kill other bacteria. They worked with a bacterium called Pseudomonas aeruginosa, isolating from it an enzyme they named piocyanase. In laboratory tests, this substance showed impressive ability to kill various disease-causing bacteria. Emmerich and Loew even attempted to use their discovery to treat infections in patients, with some reported successes. For a brief moment, piocyanase seemed poised to become the world's first practical antibiotic, but the celebration was premature. The substance proved unstable, difficult to purify, and often toxic to patients at the doses needed to kill bacteria. The treatment was unreliable, sometimes working, sometimes failing, sometimes causing reactions worse than the infections they were meant to cure. Gradually, enthusiasm waned, and piocyanase faded from medical practice, becoming a footnote in the long search for antimicrobial treatments. In England, a physician named John Burdon Sanderson had made observations as early as 1870 about how cultures contaminated with mold failed to support bacterial growth. He noted this phenomenon, but did not pursue it experimentally. Similarly, a surgeon named Joseph Lister famous for his work on antiseptic surgery, had observed in 1871 that samples of urine contaminated with mold remained free of bacteria. Lister even conducted a few experiments using Penicillin mold to treat infected wounds, though without consistent success or systematic follow-up. These scattered observations, these glimpses of nature's own weapons against bacteria, were like pieces of a puzzle, scattered across different laboratories, different countries, different decades. Each researcher saw part of the picture, but none assembled it completely. The findings were published in obscure journals, mentioned in passing in academic papers, then largely forgotten as the researchers moved on to other questions or encountered technical obstacles too difficult to overcome with the tools available to them. In Belgium, a researcher named Vuillemijn introduced the term antibiosis in 1889, providing a conceptual framework for understanding these competitive relationships between microorganisms. The word itself suggested possibility, the idea that life could be used against life, that nature might provide remedies for the diseases caused by her own tiny creatures. As the 19th century gave way to the 20th, the field of bacteriology was advancing rapidly. Scientists were identifying the specific bacteria responsible for various diseases, developing techniques to culture and study them, and beginning to understand how these microscopic organisms caused illness. Yet the practical treatment of bacterial infections remained frustratingly limited. Antiseptics could clean wounds and surfaces, but they were too toxic to use inside the body. Vaccines could prevent some diseases, but offered no help to those already infected. The pieces were slowly coming together. Scientists had discovered bacteria. They had identified these organisms as causes of disease. They had observed that some natural substances could kill bacteria. They had even, in a few cases, attempted to use these observations to treat infections. But the crucial breakthrough, the discovery that would finally unlock the practical potential of these scattered observations, still lay ahead. In laboratories across Europe, researchers continued their patient work, culturing bacteria, observing their behaviors, and occasionally noticing when something unexpected occurred. They did not know that they were living in the last years of an era, that soon the relationship between humanity and bacterial disease would change forever. The hunters of microbe-killers had glimpsed their quarry, had seen tantalizing evidence that nature held weapons against infection. Now it was only a matter of time, circumstance, and one scientist's willingness to investigate what others might have dismissed as mere contamination. The story of penicillin begins not in a laboratory, but in the green farmlands of Scotland, where a young boy would one day change the course of human history. Alexander Fleming entered the world on August 6, 1881, in Lockfield, a remote farm in Ayrshire. He was the seventh of 8 children born to Hugh Fleming, a farmer who had married twice. The landscape of his childhood was one of rolling hills, stone walls, and the constant companionship of the natural world. Young Alec, as he was known to family and friends, spent his early years roaming the countryside, developing a keen eye for observation that would later serve him well in scientific pursuits. Life on the farm taught the Fleming children patience, resourcefulness, and the ability to work with what was available. When Alec was 7 years old, his father passed away, leaving the family to manage the farm as best they could. Despite this hardship, or perhaps because of it, the children developed a remarkable independence and practical approach to solving problems. Alec attended the small rural school at Loudon Moor, walking across fields to reach his lessons, and later continued his education at Darvel School before moving to Kilmarnock Academy. At 13, Alec joined his older brothers in London, a dramatic change from the quiet Scottish countryside. The bustling metropolis must have seemed like another world entirely, with its crowded streets, factory smoke, and endless streams of people. He attended the Polytechnic on Regent Street for 2 years, and then took a job as a shipping clerk in a London office. For 4 years, Fleming worked in this mundane position, seemingly destined for an ordinary commercial career far removed from scientific discovery. But fate, or perhaps simple fortune, intervened. When Alec was 20, he received a small inheritance from an uncle. Around the same time, his older brother Tom, who had become a doctor, suggested that Alec might consider a career in medicine. It was not an obvious choice. Fleming had shown no particular fascination with healing or doctoring during his youth, yet something about the suggestion appealed to him. Perhaps the prospect of intellectual challenge or the opportunity for something more meaningful than office work. Fleming took the entrance examination for medical school, and his performance was strong enough to win him a scholarship. He chose to study at St. Mary's Hospital Medical School in Paddington, partly because he had once played water polo against their team and felt a connection to the place. It was a remarkably casual way to choose one's professional path, but it would prove to be one of the most consequential decisions in medical history. At St. Mary's, Fleming proved himself a capable if quiet student. He was not the most outgoing or charismatic among his peers, but he possessed qualities that would serve him well in research: patience, careful observation, and a willingness to notice things that others might overlook. He qualified as a doctor in 1906, and initially might have moved into private practice or general medicine. However, another stroke of fortune kept him at St. Mary's. Fleming was an excellent marksman, and the rifle club at St. Mary's wanted to keep him on their team. A member of the club who worked in the hospital's inoculation department, as it was then called, suggested that Fleming might join their research team. The chair of the department was Almroth Wright, a prominent bacteriologist and immunologist known for his work on vaccine therapy. Wright was a commanding personality, brilliant and opinionated, who gathered around him a group of dedicated researchers working on the problems of infection and immunity. Fleming accepted the position and thus began his career in bacteriology. He became a member of what was affectionately known as the Wright School, working in laboratories that were cramped, somewhat disorganized, and filled with the particular energy that comes from passionate inquiry. Wright believed in using vaccines to stimulate the body's own defenses against bacteria, and much of the laboratory work involved growing bacterial cultures, studying immune responses, and developing new approaches to prevention and treatment. The young Fleming found he had a talent for laboratory work. His farm-trained powers of observation served him well when examining bacterial cultures under the microscope. He had steady hands, essential for the delicate work of transferring and culturing microorganisms. Perhaps most importantly, he possessed what might be called a relaxed approach to laboratory tidiness. Where some researchers maintained spotlessly organized workspaces, Fleming's bench was somewhat chaotic, with culture plates often left sitting about for extended periods. This tendency toward benign neglect, which might have seemed like a flaw, would eventually prove to be the very quality that enabled his greatest discovery. During World War I, Fleming served in the Royal Army Medical Corps, working in battlefield hospitals in France alongside Almroth Wright. There he witnessed firsthand the terrible toll of infected wounds. Soldiers who survived the initial trauma of bullets and shrapnel often succumbed days later to infections that spread through damaged tissue. The antiseptics used to treat wounds, Fleming observed, sometimes did more harm than good, damaging tissue and actually hindering the body's natural defenses. He conducted experiments showing that antiseptics could not reach bacteria deep in wounded tissue, and sometimes killed helpful white blood cells, while leaving bacteria unharmed in protected pockets. These observations, published in medical journals, established Fleming as a thoughtful researcher concerned with practical problems of treatment. After the war, Fleming returned to St. Mary's and continued his work in bacteriology. He married Sarah McElroy, a trained nurse, in 1915, and they settled into a life that balanced laboratory work with Fleming's various hobbies. He was not a man of singular focus. He enjoyed art, particularly painting, and was a member of the Chelsea Arts Club. He played golf, went swimming, and maintained friendships outside the medical world. In the laboratory, he could be found hunched over his microscope for hours, but he also appreciated good conversation, dry humor, and the occasional practical joke. In 1922, Fleming made his first significant discovery. Suffering from a cold, he had the presence of mind to add a sample of his own nasal mucus to a bacterial culture plate. Days later, he noticed that the bacteria had been killed in the area where the mucus had been placed. He investigated further and discovered an enzyme, which he named lysozyme, present in tears, saliva, and other body fluids, that could break down certain bacteria. It was the body's own antibacterial agent, a natural defense that had been previously unknown. Though lysozyme proved too weak to treat serious infections, the discovery reinforced Fleming's interest in substances that could kill bacteria and demonstrated his habit of following up on unexpected observations rather than dismissing them as contamination or experimental error. By 1928, Fleming was 47 years old, an established if not particularly famous bacteriologist working in a modest laboratory in London. He had a reputation among colleagues for being observant and somewhat unconventional in his methods. His workspace remained cluttered with culture plates in various stages of growth and abandonment. He was known for sometimes leaving his work untouched for days or weeks, particularly when he took his annual vacation in Scotland. As summer gave way to autumn that year, Fleming prepared for another such holiday, leaving behind his laboratory with its usual collection of bacterial cultures sitting on the bench. He had no reason to expect that anything remarkable would happen in his absence, but the particular combination of his working habits, the London weather, and simple chance was about to create the conditions for one of the most important accidents in scientific history. The summer of 1928 had been particularly pleasant in London, and Alexander Fleming, like many who could manage it, had taken the opportunity to escape the city for a holiday. He and his family retreated to the countryside, away from the laboratory benches and petri dishes that occupied so much of his daily life. The decision to leave in early August was not unusual for Fleming. He had always valued his time away from work, whether pursuing his hobby of painting or simply enjoying the company of friends and family. The laboratory at St. Mary's Hospital could wait, but laboratories, as it happens, do not truly wait. They continue their invisible processes, their chemical reactions, their biological dramas, even when no human eye is present to observe. In Fleming's absence, the plates of bacterial cultures he had been working with before his departure sat undisturbed on his cluttered workbench. The windows of his second-floor laboratory remained as they often were, open to the London air. Below, on the floor beneath, other researchers continued their own investigations into the mysteries of microorganisms. When Fleming returned to his laboratory in early September, he faced the familiar task that greets any researcher after an absence, sorting through the work left behind. The Staphylococcus cultures he had been growing before his holiday had served their purpose, and now they needed to be cleaned away to make room for new experiments. These golden-colored bacteria, familiar enemies of human health, had been the subject of his investigation, and Fleming had inoculated numerous petri dishes with them before departing. As Fleming began examining the culture plates stacked on his bench, preparing to sterilize and discard them, something caught his attention. One plate looked different from the others. Around a spot of mold contamination, something remarkable had occurred. The Staphylococcus bacteria, which should have formed a uniform golden carpet across the agar surface, had been destroyed. Around the mold colony, a clear zone had formed, a halo of emptiness where no bacteria grew. For most researchers, contamination represented nothing more than frustration, a ruined experiment requiring the disposal of spoiled cultures. Fleming's laboratory was notoriously untidy, and mold contamination was not an unusual occurrence in the bacteriology labs of the time. The standard response would have been to discard the plate immediately, sterilize it, and move on, but Fleming did not discard the plate. What made him pause, perhaps it was his years of careful observation, the trained eye that had served him well in his previous research on antiseptics and the body's natural defenses. Perhaps it was simple curiosity, that quality essential to all scientific discovery. Whatever the reason, Fleming recognized that something unusual had happened on this particular plate. The pattern of bacterial death around the mold was too distinct, too pronounced to ignore. He called over a colleague who was working nearby. The exact words of that moment have been debated by historians, but the essence remains clear. Fleming wanted another pair of eyes to confirm what he was seeing. The clear zone around the mold was not imagination or artifact. Something produced by that mold had killed the bacteria or prevented their growth. The contamination that should have been merely annoying had become deeply interesting. The mold itself was not particularly impressive to look at. It appeared as a fluffy growth, somewhat greenish in color, the kind of fungus that might appear on forgotten bread or overripe fruit, but its effect on the surrounding bacteria was dramatic. The Staphylococcus, normally so robust and quick to multiply, had been destroyed in a circular pattern radiating outward from the mold colony. The zone of destruction was clear and unmistakable. Fleming's decision to preserve this contaminated plate rather than discard it represents one of those pivotal moments where scientific progress hangs on individual choice. How many similar plates had been thrown away by other researchers over the years, their potential significance never recognized? How many times had mold-contaminated bacterial cultures in laboratories around the world, only to be dismissed as nuisance rather than investigated as opportunity? The circumstances that had led to this particular contamination were themselves a chain of unlikely events. The mold spores had likely drifted up from the laboratory on the floor below, where researchers were studying fungi. The open window of Fleming's laboratory had provided entry. The timing of the contamination, occurring just before Fleming's departure, allowed the mold to establish itself on the plate. The weather during his absence, cooler than usual for August, had created conditions favorable for both mold growth and the production of whatever substance was killing the bacteria. Had Fleming returned a few days earlier or later, had the weather been different, had the window been closed, the observation might never have been made. Fleming carefully preserved the contaminated plate, protecting it from further disturbance. He recognized immediately that this observation warranted serious investigation. What was the mold producing that could destroy bacteria? Could this substance be isolated and studied? Might it have practical applications? The questions multiplied in Fleming's mind as he examined the plate more closely. The mold had created something powerful enough to kill Staphylococcus, bacteria that were responsible for countless human infections, from minor skin ailments to life-threatening blood poisoning. If this mold-produced substance could be understood, controlled, and perhaps applied deliberately, it might offer exactly the kind of selective antibacterial agent that researchers had been seeking for decades. Fleming set about identifying the mold itself. He took samples and began the process of growing pure cultures of the fungus, separating it from any bacterial contamination. The mold needed a name, an identity. Through careful examination and consultation with mycology experts, the organism was identified as belonging to the genus Penicillium, a common group of molds found throughout the environment. The specific species was initially thought to be Penicillium rubrum, though later analysis would revise this identification to Penicillium notatum. That September observation, made possible by a concatenation of fortunate accidents and Fleming's decision to look closely rather than look away, marked the beginning of the penicillin story. The contaminated plate, which should have been nothing more than laboratory waste, had become a window into possibility. Fleming could not have known, standing in his cluttered laboratory that September day, how profoundly this moldy dish would eventually reshape medicine. He knew only that something remarkable had happened, and that it deserved investigation. The stage was set for the work that would follow. The questions now was whether this observation could be transformed into understanding, and whether understanding could be transformed into something useful for humanity. In the days following his return from vacation, Alexander Fleming found himself drawn back to that curious contaminated plate again and again. The mold colony sat there like a small island in a sea of bacterial culture, and around it stretched that clear zone where no bacteria grew. For many researchers, the story might have ended with the initial observation, perhaps a passing mention in a laboratory notebook. But Fleming possessed a quality that separated remarkable scientists from merely competent ones. He paid attention to the unexpected. He began his investigation methodically, transferring a sample of the mold to a fresh culture medium where it could grow without competition. The fungus spread slowly across the surface, developing its characteristic blue-green appearance with white edges. Fleming noted everything: the color, the texture, the rate of growth. He was like a naturalist documenting a newly discovered species, which in a sense he was. The mold needed identification, and after consultation with a mycologist in the floor below his laboratory, it was determined to belong to the genus Penicillium, those common molds that grow on aging bread and forgotten fruit. The real question that intrigued Fleming was not the mold itself, but what it produced. Something released by that fungus was killing bacteria, and he wanted to understand this invisible weapon. he began growing the mold in liquid broth, allowing it to multiply and presumably to release whatever antibacterial substance it manufactured. After the mold had grown for several days, he carefully filtered the liquid to remove all the fungal material, leaving only the clear broth in which the penicillium had lived. This filtered liquid became his experimental tool. Fleming tested it against various types of bacteria, adding drops of the broth to different bacterial cultures to see what would happen. The results fascinated him. The substance proved remarkably effective against many of the bacteria that caused common human infections: Staphylococci, Streptococci, Pneumococci, and others that physicians encountered daily in their patients. Yet curiously, it had little effect on certain other bacterial species. This selectivity was itself intriguing, suggesting that whatever the mold produced, it worked through a specific mechanism, rather than simply poisoning everything it touched. Fleming began referring to this mysterious antibacterial substance as mold juice in casual laboratory conversation, though he would later adopt the more scientific name, penicillin. Derived from the penicillium mold that produced it, he conducted experiments to understand its properties, testing how stable it remained under different conditions. He found that heat destroyed it, as did strong acids or alkaline solutions. The substance seemed frustratingly delicate, losing its potency when exposed to conditions that were too far from neutral. In one particularly significant series of experiments, Fleming tested whether penicillin might be toxic to human cells and tissues. Using techniques available in his laboratory, he exposed white blood cells and other human tissues to the broth containing penicillin. The results encouraged him greatly. Even in concentrations strong enough to kill bacteria, the substance showed no harmful effects on human cells. This suggested the tantalizing possibility that penicillin might be used to treat infections in living patients without poisoning them in the process. Fleming also discovered that penicillin could be diluted considerably and still retain its bacteria-killing properties. He found that even when diluted to 1 part in 500, or in some experiments as much as 1 part in 800, the broth still prevented bacterial growth. This remarkable potency suggested that whatever chemical compound the mold produced, it was extraordinarily effective at very low concentrations. Throughout late 1928 and into 1929, Fleming continued his investigations, filling notebook pages with observations and results. He attempted to use penicillin as a laboratory tool, taking advantage of its selective properties. Since it killed some bacteria but not others, he could add it to mixed cultures to eliminate unwanted bacterial species while allowing others to grow. This practical application proved useful in his bacteriology work, and he shared samples of his mold with colleagues who found similar uses for it. Yet Fleming faced a significant obstacle that would ultimately limit his work with penicillin. He was a bacteriologist, skilled in growing and studying microorganisms, but he lacked expertise in chemistry. Extracting and purifying the active substance from the mold broth required chemical knowledge and techniques beyond his training. He made some attempts, working with a young researcher named Frederick Ridley and a biochemistry student named Stuart Craddock, but their efforts to isolate pure penicillin met with limited success. The substance proved maddeningly difficult to separate from the broth in which it grew. It was unstable, losing potency during the extraction process. The amount they could produce remained small, and the pure compound seemed to deteriorate quickly even when they managed to concentrate it. Without purified penicillin in stable form, the possibility of using it as a medicine remained distant. Fleming could demonstrate its antibacterial properties in laboratory dishes, but translating that to treating actual infections in patients would require far more of the substance in far purer form than he could produce. In 1929, Fleming published his findings in the British Journal of Experimental Pathology. The paper described his observations of the penicillium mold, documented its antibacterial properties, and suggested possible applications. He wrote in his characteristically understated style, presenting the facts without dramatic claims. The paper mentioned the possibility that penicillin might be useful for treating infections, but Fleming emphasized its laboratory applications more strongly, perhaps recognizing the practical difficulties that stood between his laboratory observations and clinical use. The publication generated little immediate excitement in the medical community. Fleming presented his work at a meeting of the Medical Research Club, where it was received with polite interest but no particular enthusiasm. The few researchers who did pay attention saw penicillin primarily as Fleming did, a useful laboratory tool for isolating certain bacteria, rather than a potential medicine. The paper was read, noted, and largely set aside as the scientific community moved on to other matters. Fleming himself continued to maintain his penicillium culture, keeping it alive in his laboratory, and occasionally using it for bacterial isolation work. He would grow more of the mold when he needed it, extract some of the broth, and use it in his ongoing research. But without the chemical expertise to purify it, and without clear evidence that it could work in living bodies rather than just laboratory dishes, he could pursue the discovery no further. The remarkable substance remained a curiosity, a promising observation, waiting for someone with the right skills and resources to unlock its potential. Fleming's discovery had been announced to the world. His paper, published in 1929, described the remarkable properties of the mold juice he called penicillin. He had demonstrated its ability to kill dangerous bacteria while showing relatively little toxicity to animal tissue. The scientific community had been informed. The door to a new era of medicine stood open, waiting for someone to walk through it. But no one came. The years following Fleming's publication passed with surprising quiet, while the world outside the laboratory walls experienced the economic turmoil of the Great Depression. While political tensions mounted across Europe, the peculiar substance from Fleming's contaminated culture plate gathered dust in the corridors of scientific inquiry. Fleming himself continued his work at St. Mary's Hospital, maintaining cultures of the penicillium mold, occasionally mentioning his discovery in lectures, but the spark of 1928 failed to ignite the enthusiasm he had hoped for. The reasons for this dormancy were numerous and interconnected, each one a small obstacle that together formed an insurmountable wall. Fleming had shown that penicillin worked beautifully in laboratory dishes, killing bacteria with impressive efficiency. He had even demonstrated some limited uses, such as applying it to surface infections and using it to isolate particular bacteria by killing off their competitors. Yet the crucial leap from laboratory bench to patient's bedside remained unmade. The technical challenges loomed largest. Penicillin proved to be an extraordinarily difficult substance to work with, but existed in the mold broth in tiny concentrations, mixed with all manner of other substances the mold produced. Extracting it, concentrating it, and purifying it required chemical expertise that Fleming's laboratory lacked. His filtrate worked well enough for growing in Petri dishes, but achieving the purity and concentration needed for injecting into human patients was another matter entirely. Moreover, penicillin demonstrated an almost mischievous instability. It degraded rapidly under various conditions, losing its antibacterial power seemingly at whim. Heat destroyed it. Certain chemical treatments destroyed it. Even storing it presented challenges. The substance that seemed so powerful against bacteria proved frustratingly fragile in the hands of researchers. Working with penicillin felt like trying to grasp water, the precious substance slipping away before it could be properly harnessed. Fleming had tried to interest chemists in the purification problem. He spoke with colleagues, mentioned the challenge to various researchers, but the response remained tepid. Chemists in the late 1920s and early 1930s faced no shortage of interesting problems to solve. The new field of biochemistry was exploding with discoveries. Vitamins were being isolated and characterized. Hormones were revealing their secrets. The structure of proteins beckoned as a grand challenge. Penicillin, unstable and present in such minute quantities, simply did not capture sustained attention. The medical context of the time also contributed to penicillin's dormancy. While bacterial infections certainly killed and maimed, the 1930s saw the introduction of the sulfonamide drugs, the first truly effective antibacterial medicines. These synthetic compounds, beginning with Prontosil in 1935, could be manufactured chemically, with no need to coax temperamental molds into producing uncertain quantities of unstable substances. The sulfonamides worked against many important bacterial infections, and pharmaceutical companies could produce them reliably. Why struggle with a difficult natural product when chemistry offered a cleaner path forward? Fleming himself bore some responsibility for the quiet years, though through no fault of character or commitment. His personality, so well suited to the observant patience that had led to penicillin's discovery, did not lend itself to aggressive promotion and salesmanship. He was not one to pound on doors or lobby forcefully for resources and attention. He mentioned penicillin in his lectures, certainly. He published his findings, definitely, but the theatrical advocacy that might have captured imaginations and loosened research funding remained foreign to his nature. Still, the mold cultures lived on at St. Mary's Hospital. Fleming maintained them carefully, occasionally providing samples to researchers who expressed interest. A few scientists did take notice, conducting small investigations that added modest pieces to the puzzle. In 1932, a researcher named Payne used penicillin to successfully treat eye infections in infants, achieving impressive results with this external application. The success suggested medical potential, yet even this practical demonstration failed to generate broader investigation. Another researcher, Raystrick, attempted to purify and characterize penicillin in the early 1930s, making some progress in understanding its chemical properties, but ultimately abandoning the work as too difficult. Each small effort added a fragment of knowledge, then faded away, leaving penicillin in its curious limbo between recognized potential and practical reality. The scientific literature of these quiet years shows occasional references to Fleming's discovery. A citation here, a mention there, like distant echoes of the original finding. Penicillin had not been forgotten entirely, but neither had it captured the sustained, focused attention necessary to overcome the formidable obstacles between laboratory curiosity and medical treatment. Fleming continued his other research pursuits, investigating various aspects of bacteriology and immunology. He was a productive scientist with interests beyond penicillin, yet he never fully abandoned his first great discovery. The cultures were maintained, the knowledge preserved, waiting for circumstances to change. The world moved through these years with gathering momentum toward conflict. Political situations darkened, military buildups accelerated. The Depression slowly loosened its grip on economies, even as international tensions tightened, and in laboratories scattered across several countries, researchers continued their work on bacterial diseases, on chemical compounds, on the fundamental questions of how living systems functioned. Penicillin remained available to anyone who might want to investigate further. Fleming would provide samples. His publications could be found in any good medical library. The door still stood open, waiting. The mold grew in its cultures, producing its antibacterial substance, as it had for millions of years before a laboratory accident had brought it to human attention. As the 1930s drew toward their close, as Europe moved inexorably toward war, penicillin remained a footnote in bacteriology, a curious finding that had somehow failed to flourish. The quiet years stretched on, each one carrying the substance further from its moment of discovery, deeper into obscurity. But in Oxford, two scientists were beginning to think about old problems in new ways. They were reviewing the literature on natural antibacterial substances, compiling information, considering possibilities. They would soon encounter Fleming's publications from a decade earlier, and when they did, the quiet years would finally come to an end. The late 1930s brought together two remarkable minds in the laboratories of Oxford University, each carrying vastly different experiences and perspectives, yet both sharing an intense dedication to understanding the chemistry of life itself. Their partnership would breathe new life into Fleming's forgotten discovery and transform it from a curious laboratory observation into something that would reshape the future of medicine. Howard Walter Florey arrived at Oxford in 1935 as the newly appointed professor of pathology. Born in Adelaide, Australia in 1898, Florey had journeyed far from his homeland to pursue medical research. He possessed a practical, no-nonsense approach to science, combined with exceptional organizational skills and an ability to assemble talented research teams. Florey's Australian upbringing had instilled in him a directness and efficiency that sometimes made him seem brusque to his English colleagues. But beneath this exterior lay a brilliant mind capable of seeing how different pieces of research might fit together to solve complex problems. Florey had studied at Oxford as a Rhodes Scholar in the 1920s, then worked in Cambridge and Sheffield, before returning to Oxford to lead the Sir William Dunn School of Pathology. He understood not just the scientific challenges of medical research, but also the administrative and financial complexities of running a productive laboratory. This combination of skills would prove essential in the years ahead. Ernst Boris Chain entered Florey's world through a more circuitous route. Born in Berlin in 1906 to a Russian Jewish family, Chain had initially pursued music, showing considerable talent as a pianist. But science captured his imagination, and he earned his degree in chemistry and physiology from Friedrich Wilhelm University in Berlin. The rise of the Nazi regime in Germany forced Chain to flee his homeland in 1933, leaving behind his family and the life he had known. He arrived in England as a refugee, carrying little but his scientific training and his determination to continue his research. Chain found work first at Cambridge, then joined Florey's department at Oxford in 1935. Where Florey was practical and organized, Chain brought passionate intensity and deep knowledge of biochemistry. He possessed a gift for understanding the complex chemistry of biological substances, and he approached problems with creative enthusiasm that sometimes clashed with Florey's more methodical style. Yet their differences complemented each other remarkably well. By 1938, Florey and Chain were searching for a project that would make good use of their combined expertise. Florey had long been interested in substances produced by the body that could fight infection, and Chain's biochemical skills seemed perfectly suited to isolating and identifying such substances. They began reviewing the scientific literature, looking for promising leads that others might have overlooked. Chain came across Fleming's 1929 paper describing the antibacterial properties of the Penicillin mold. The paper intrigued him for several reasons. Fleming had clearly demonstrated that the mold produced something that killed bacteria, yet the substance remained chemically mysterious. Was it an enzyme, as Fleming had suggested? What was its chemical structure? How did it work? These questions appealed to Chain's biochemical curiosity. Florey saw different possibilities in Fleming's old paper. If this penicillin substance could be isolated and purified, might it have practical medical applications? The technical challenges that had discouraged others seemed surmountable. With the right combination of skills and resources, Chain could handle the complex biochemistry, and Florey knew how to organize the necessary team and equipment. The Oxford laboratory had another advantage. Florey had assembled a small but talented group of researchers, each bringing specialized skills. Norman Heatley, a quiet and ingenious biochemist, possessed remarkable practical abilities in designing and building laboratory equipment. Arthur Duncan Gardner contributed expertise in bacteriology. Margaret Jennings, who would later become Florey's second wife, brought careful experimental design and execution to the team. Together they represented a formidable combination of talents. In 1939, the team began their work on penicillin, with no sense that they were embarking on anything world-changing. Their initial goal was simply to understand what this mysterious substance was and how it worked. They approached it as a scientific puzzle worth solving, another investigation in the ongoing effort to understand how living organisms defend themselves against infection. The timing, though coincidental, would prove significant. As Florey and Chain organized their assault on penicillin's mysteries, Europe was sliding toward war. Within months of their project's beginning, Britain would be at war with Germany, adding urgency and meaning to any research that might help treat infected wounds. But in those first months, the Oxford team worked in relative peace, setting up their equipment, reviewing Fleming's methods, and planning their experiments. Chain began by trying to reproduce Fleming's results, growing the penicillium mold and testing its effects on bacteria. The early work confirmed what Fleming had reported. Something in the mold broth definitely killed bacteria. The challenge now was to capture that something in pure form, to isolate it from all the other substances present in the liquid where the mold grew. This task would prove far more difficult than anyone anticipated. Penicillin turned out to be remarkably unstable, losing its bacteria-killing power when exposed to heat, acids, or various other conditions. It existed in tiny concentrations in the mold broth, mixed with countless other substances. Separating and purifying it would require innovation, patience, and techniques that would need to be invented as the work progressed. but the Oxford team had qualities that the earlier investigators of penicillin had lacked. They had a biochemist of Chain's caliber, a leader with Florey's organizational skills, and a team with complementary abilities. They had access to resources and equipment. Most importantly, they approached the problem with determination and the expectation that obstacles existed to be overcome, not accepted. As 1939 drew to a close, and the first winter of the war settled over Oxford, the team worked late into the evenings in their laboratory, gradually developing methods to coax the unstable penicillin molecule out of solution and into forms they could study and test. The work was painstaking, progress measured in tiny increments, but they were making progress, moving penicillin forward from where Fleming had left it a decade earlier. In these quiet months, before the dramatic breakthroughs and eventual worldwide impact, the foundation was being laid for everything that would follow. Two scientists from opposite sides of the world had found each other, found a promising mystery, and committed themselves to solving it. The problem that Howard Florey and Ernst Boris Chain faced in their Oxford laboratory was both deceptively simple and monumentally difficult. Fleming had discovered that a particular mold could kill bacteria. That much was known. But between a moldy petri dish and a medicine that could save human lives stretched a vast wilderness of technical challenges that would demand every ounce of their ingenuity and determination. The substance that Fleming had called penicillin existed in vanishingly small quantities in the broth where the penicillium mold grew. To obtain even a tiny amount of the purified active ingredient, the Oxford team would need to process enormous volumes of this liquid. It was rather like trying to extract a few grains of sugar from an Olympic swimming pool of water, except that penicillin was far more delicate and unstable than sugar, liable to lose its bacteria-killing properties at the slightest mishandling. In those early months of 1939 and 1940, the laboratory on the top floor of the Sir William Dunn School of Pathology became a peculiar sort of factory. Norman Heatley, a biochemist with a remarkable talent for improvising equipment, joined Florey and Chain in their quest. Together they transformed the academic laboratory into something resembling a medieval alchemist's workshop crossed with a dairy. The first challenge was growing enough mold to work with. The team began cultivating Penicillium notatum, the same species Fleming had studied, in flat-sided glass vessels that looked rather like hospital bedpans. These vessels, stacked and arranged throughout the laboratory, soon numbered in the hundreds. Each one contained a thin layer of culture broth where the mold could grow on the surface. The laboratory took on the musty, slightly sweet smell of the growing fungus, a scent that would become intimately familiar to everyone working there. Heatley proved to be an absolute wizard at creating equipment from whatever materials were at hand. With laboratory supply budgets stretched thin and war looming on the horizon, he fashioned extraction apparatus from rubber tubing, tin cans, and even parts salvaged from a local junkyard. He designed a clever contraption using old bookcases and ceramic containers to increase the surface area for growing the mold, where expensive commercial equipment would normally be specified. Heatley invented alternatives that cost pennies, but worked just as well. Once the mold had grown sufficiently, the real challenge began. The team needed to separate the penicillin from the complex mixture of proteins, sugars, and other substances in the culture broth. Chain, drawing on his training in biochemistry, developed a painstaking extraction process. The technique involved adjusting the acidity of the liquid, then using organic solvents to pull the penicillin out of the watery broth. Ether proved particularly useful for this purpose, though working with such a volatile and flammable solvent required constant caution. The process had to be carried out quickly and at low temperatures. Penicillin, they discovered, was frustratingly unstable. It would break down if the solution became too acidic or too alkaline. Heat destroyed it. Even storing it for too long could render it useless. The substance they were chasing seemed to have the consistency and permanence of a snowflake, beautiful and powerful but liable to vanish at any moment. Day after day, the team worked through cycles of growing mold, harvesting the broth, and attempting to extract the precious substance. The yield was heartbreakingly small. Processing hundreds of liters of culture broth might produce only enough penicillin to treat a single patient for a single day. The brown powder they eventually obtained looked unpromising, almost dirty, but when tested against bacteria, it showed remarkable potency. The work was tedious and exhausting. Research assistants spent hours tending the mold cultures, carefully pouring off the liquid at just the right moment, maintaining precise conditions of temperature and acidity. The extraction itself required round-the-clock attention. Penicillin didn't respect normal working hours, and if a batch was ready for the next stage of processing at midnight, someone needed to be there to handle it or risk losing the entire effort. As 1940 progressed, the team gradually refined their methods. They learned tricks for coaxing slightly higher yields from each batch. They discovered that certain modifications to the culture medium helped the mold produce more of the active substance. Heatley developed a better extraction system using amyl acetate, which proved somewhat more efficient than ether. Each small improvement felt like a victory. Though the fundamental problem remained, they could produce penicillin in their laboratory, but only in amounts that could be measured in milligrams. The question hanging over everything was whether this substance, so difficult to obtain, would actually work in a living creature. The chemical tests were promising. The experiments with bacteria in test tubes looked excellent, but human bodies were far more complex than glassware. Would penicillin be toxic? Would it maintain its bacteria-killing power inside a living system? Would the body break it down before it could do any good? By the spring of 1940, Florey decided they had accumulated enough material to attempt animal trials. The team had perhaps a thimbleful of partially purified penicillin, represented by months of exhausting labor. It was barely enough, but the question was too important to delay any longer. They needed to know if this substance could actually fight infection in a living creature. The experiments with mice would come next, small creatures serving as surrogates for the ultimate question of whether this moldy miracle could save human lives. But even preparing for those trials, the Oxford team understood that they were bumping against the limits of what an academic laboratory could achieve. The extraction challenge wasn't fully solved. It was merely managed, barely, through extraordinary effort and clever improvisation, to produce penicillin in quantities that could make a real difference in the world. They would need something far beyond what their rooftop laboratory could provide. The technical obstacles they had overcome were just the beginning of a much longer journey. As evening fell over Oxford and the laboratory windows grew dark, the work continued by lamplight, the smell of mold and solvents hanging in the air, and the promise of something extraordinary growing stronger with each carefully extracted grain of brown powder. After months of painstaking extraction work in their Oxford laboratory, Howard Florey and Ernst Boris Chain finally possessed enough purified penicillin to attempt what had never been done before, treating a human patient with a serious bacterial infection. The year was 1941, and the world around them was at war. But in the quiet corners of their research facility, a different kind of battle was about to begin. The opportunity arrived on a cold February day when word reached the Oxford team about a patient at the Radcliffe Infirmary. Albert Alexander was a 43-year-old police constable who had been tending his rose garden when a thorn scratched his face near his mouth. In an age before antibiotics, such a minor injury could become a death sentence, and that is precisely what was happening to this unfortunate man. The small scratch had become infected, and the infection had spread with frightening speed. By the time the researchers heard about him, Alexander had been suffering for months. The bacterial invasion had created abscesses on his face and scalp. His eyes were swollen, and one had to be removed in a desperate attempt to stop the infection's advance. The bacteria had entered his lungs and shoulders. Despite receiving all the conventional treatments available, including sulfonamide drugs, his condition continued to deteriorate. The medical staff caring for him had exhausted their options. Florey and his colleague, a young doctor named Charles Fletcher, visited Alexander in the hospital. What they found was a man in desperate straits, his body ravaged by an infection that conventional medicine could not control. Yet this same terrible condition made him an ideal candidate for their experimental treatment. If penicillin could help someone this gravely ill, it would demonstrate powers beyond anything currently available. The decision to proceed was not taken lightly. The Oxford team knew their purified penicillin had worked remarkably well in mice, but human bodies were far more complex. They discussed dosing strategies, knowing that their supplies were painfully limited despite months of production effort. Every drop of the precious substance would have to be used wisely. On the 12th of February, 1941, Charles Fletcher administered the first injection of penicillin into Albert Alexander's vein. The dose was small by later standards, just 200 milligrams, but it represented an enormous quantity given how difficult penicillin was to produce. The team then continued with injections every 3 hours, carefully monitoring their patient for any reaction. What happened next seemed almost miraculous. Within 24 hours, Alexander's fever began to drop. His appetite returned, something that had been absent for weeks. The swelling in his remaining eye decreased noticeably. By the second day, the improvement was unmistakable. The abscesses began to heal, and the constable appeared to be pulling back from the edge of death. He was able to speak with his caregivers, expressing relief at feeling better for the first time in months. The transformation was so dramatic that it energized everyone involved in the treatment. It was tangible proof that penicillin could do in humans what it had accomplished in laboratory animals. The substance was attacking the bacterial infection with a power that existing medicines could not match. Fleming's observation in a petri dish, Chain's biochemical investigations, and Florey's determination to develop a practical treatment were all vindicated in the improving condition of this one policeman. Yet even as hope loomed, a shadow loomed over the case. The Oxford team faced a problem they had anticipated, but hoped to avoid. Their stocks of penicillin were running dangerously low. Despite having converted much of their laboratory into a production facility, despite the bottles and bedpans and ceramic vessels all pressed into service growing mold, despite months of labor by their assistants extracting and purifying the precious substance, they simply could not make enough. The researchers took an extraordinary step to stretch their limited supplies. They collected Alexander's urine, knowing that much of the penicillin passed through his body, relatively unchanged. Working quickly, they extracted penicillin from the urine and purified it for re-injection. This recycling process was tedious and recovered only a portion of what had been administered, but every unit counted when supplies were measured in such tiny quantities. For 5 days, the treatment continued, and Albert Alexander continued to improve. The team allowed themselves to believe they were witnessing the beginning of a new era in medicine. But on the 5th day, their worst fears materialized. The penicillin ran out completely. They had used everything they possessed, extracted every possible drop from the patient's urine, and there was simply no more available. Production facilities back at their laboratory were working at full capacity, but growing the mold and extracting the active substance took time they did not have. Without continued treatment, Alexander's condition began to reverse. The infection, which had been beaten back but not eliminated, began to advance once more. The researchers could only watch helplessly as the brief window of hope closed. Despite the dramatic improvement he had shown, despite the clear evidence that penicillin was fighting his infection effectively, Albert Alexander died on the 15th of March, just weeks after his treatment had begun. The loss was devastating to everyone involved, particularly to Fletcher, who had overseen the treatment directly. Yet even in this tragedy, the experiment had revealed crucial information. Penicillin worked in humans just as it did in mice. It could fight severe infections that defeated other treatments. A man who had been dying had shown remarkable improvement when the drug was available. The problem was not whether penicillin could save lives, but whether enough could be produced to complete treatments. The team immediately began treating other patients, carefully selecting cases where smaller amounts of penicillin might suffice. A 15-year-old boy with an infection following hip surgery recovered completely. A young child with a severe bloodstream infection survived. These cases required less penicillin than Alexander's advanced condition had demanded, and the treatment succeeded. The constable's case, despite its tragic ending, had demonstrated beyond any doubt that penicillin represented something extraordinary. The urgent question now was not whether penicillin should be developed, but how production could be scaled up to meet the tremendous need. In a world at war, with wounded soldiers facing infected injuries by the thousands. The race to manufacture penicillin in meaningful quantities became a matter of life and death for countless individuals beyond the walls of one Oxford hospital. The policeman's case had shown what penicillin could do, but it had also revealed the heartbreaking reality of insufficient supply. As spring arrived in 1941, the Oxford team returned to their laboratories with renewed determination, knowing they possessed something extraordinary yet frustratingly scarce. They could save lives, but only if they could produce enough of the precious substance. The work continued in their modest facilities, extracting penicillin drop by precious drop, treating a handful of additional patients with carefully conserved supplies. But beyond the quiet corridors of Oxford University, the world was consumed by conflict. The war that had begun in September 1939 was expanding across continents, drawing more nations into its devastating embrace. By 1941, the fighting stretched from the deserts of North Africa to the cities of Europe, from the Atlantic Ocean to the vast expanses of the Soviet Union. And with this expansion came casualties on a scale difficult to comprehend, creating medical challenges that traditional treatment simply could not address. Every battlefield produced wounded soldiers by the thousands. Unlike the clean, controlled environment of a hospital, these injuries occurred in the mud and dirt of trenches, in the sand of deserts, amid the debris of shattered buildings. Bullets and shrapnel tore through flesh, creating wounds that became contaminated with soil, fabric, and bacteria. Even soldiers who survived the initial trauma of their injuries faced another enemy that was invisible but equally deadly: infection. Military surgeons found themselves fighting a losing battle against sepsis and gangrene. They could remove bullets, set broken bones, and stitch torn tissue, but they had no effective weapon against the bacteria that invaded every wound. Sulfur drugs, the best antibacterial agents available, worked against some infections, but were powerless against many others. Young men who might have recovered from their injuries died instead from infections that turned wounds septic, poisoned blood, or destroyed tissue beyond repair. The statistics were sobering. Medical officers calculated that infections were responsible for a significant portion of battlefield deaths and an even larger percentage of prolonged hospitalizations. Soldiers who contracted gas gangrene faced particularly grim prospects, with the infection spreading rapidly through tissue and often requiring amputation as the only hope of saving life. Even with amputation, survival was far from certain. Pneumonia, which developed in soldiers weakened by wounds or exposed to harsh conditions, remained a major killer in military hospitals. This medical crisis did not escape the attention of military leadership and government officials. Wars are won not just by weapons and strategy, but by the ability to return wounded soldiers to health, to maintain fighting forces, and to preserve the lives of valuable trained personnel. Every soldier lost to infection was a soldier who could not return to duty, who required prolonged medical care, and whose death affected morale both at the front and at home. The traditional acceptance of infection as an inevitable consequence of war was giving way to a new understanding that medical innovation might offer solutions. If scientists could develop better treatments for infected wounds, the impact on military effectiveness would be substantial. Survival rates would improve, recovery times would shorten, and fewer soldiers would face amputation or permanent disability. The potential benefits extended beyond individual lives to strategic military advantage. In this context, news of the Oxford team's work with penicillin began to attract attention from those in positions to help. The successful treatment of patients, even in small numbers, demonstrated capabilities that military medicine desperately needed. Here was a substance that could attack the very bacteria causing wound infections, that worked where other treatments failed, that offered hope for conditions previously considered fatal. The urgency of war created a different kind of momentum than peacetime research had generated. Questions that might have taken years to work through in normal circumstances suddenly demanded immediate answers. Could penicillin be produced in larger quantities? Could it treat the specific types of infections most common in battlefield wounds? How stable was it under field conditions? Could it be administered effectively in military hospitals near the front lines? Howard Florey and his colleagues found themselves in conversations with military medical officers, with government representatives, with officials who understood that this scientific curiosity might hold the key to saving thousands of lives. The quiet academic research that had characterized their work was transforming into something with implications for national survival. The challenge, however, remained formidable. The methods they had developed in Oxford could produce enough penicillin to treat perhaps a few dozen patients. The military needed enough to treat thousands, perhaps tens of thousands. The gap between what they could accomplish in their laboratory and what the war demanded seemed almost unbridgeable. British pharmaceutical companies approached about scaling up production were stretched thin by wartime demands. Factories that might have turned to penicillin production were already committed to producing other essential medicines, explosives, and military supplies. The bombing raids that German aircraft conducted over British cities created additional complications, threatening facilities and disrupting normal operations. Resources were scarce, priorities were competing, and the technical challenges of large-scale penicillin production remained unsolved. Yet the need continued to grow more urgent with each passing month. As 1941 progressed, the war intensified. Germany invaded the Soviet Union in June, opening a vast new front with casualties mounting into the hundreds of thousands. In North Africa, British forces fought back and forth across desert terrain, with wounded soldiers transported to field hospitals where infection remained the constant enemy. At sea, naval engagements produced their own casualties, with injured sailors facing the additional challenge of wounds contaminated by seawater. The Oxford team understood that their small-scale production methods would never meet this enormous need. They could continue treating individual patients, documenting penicillin's effectiveness, and refining their techniques, but this would not address the crisis unfolding across the war zones. Something more was needed: industrial-scale production, resources beyond what Britain could provide in wartime, and perhaps assistance from beyond Britain's shores. The war had created the desperate urgency that peacetime had lacked. It had transformed penicillin from a promising laboratory finding into a potential tool for saving the lives of soldiers fighting for their nation's survival. The question was no longer whether penicillin was valuable, but how to produce enough of it to make a difference in a world at war. The summer of 1941 found Howard Florey facing an impossible situation. The Oxford laboratory had proven beyond doubt that penicillin could save lives, yet they could barely produce enough of the substance to treat a single patient completely. The glassware and milk bottles that lined every surface of their laboratory, the bedpans pressed into service as culture vessels, the constant labor of extracting minuscule amounts of the precious substance, all of it represented the absolute limit of what their small team could accomplish. Meanwhile, the war continued to create an endless stream of wounded soldiers who needed treatment, and Britain's resources were stretched desperately thin. Florey understood that if penicillin was to fulfill its promise, the challenge had shifted from scientific discovery to industrial production. This was no longer a problem that could be solved in a university laboratory, with clever experiments and dedicated researchers. It required manufacturing expertise, industrial facilities, and resources on a scale that wartime Britain simply could not provide. The factories were busy with munitions, the chemists were occupied with military projects, and the pharmaceutical companies that might have helped were already working at capacity on other war efforts. So Florey made a decision that would prove crucial to the penicillin story. He would travel to America, carrying with him the knowledge accumulated through years of painstaking work, and seek the help needed to transform penicillin from a laboratory marvel into a medicine that could be produced in meaningful quantities. The journey itself was not without risk. German submarines prowled the Atlantic, and crossing the ocean in 1941 meant accepting genuine danger. Florey traveled with Norman Heatley, the biochemist whose ingenious extraction methods had made their Oxford work possible. They carried with them detailed notebooks, scientific papers, and perhaps most preciously, samples of their Penicillium mold strain carefully preserved in the event that all other records might be lost. There's a rather charming detail about this precious cargo. Concerned that their mold cultures might be confiscated or destroyed if their ship were attacked, They smeared some of the penicillium into the lining of their coat pockets. If everything else was lost, they reasoned, they could at least salvage the living organism that produced penicillin from their clothing. This small act illustrated the peculiar combination of scientific dedication and practical improvisation that characterized. They arrived in America in early July, stepping into a country not yet at war, but already sensing the approaching conflict. Their first stop was the Rockefeller Foundation in New York, where Florey had connections from his earlier research career. The foundation had supported medical research for decades, and its officials understood immediately the significance of what Florey described. Within days, arrangements were made for meetings with the right people: pharmaceutical company executives, government officials, and researchers who specialized in fermentation and large-scale production of biological materials. The critical connection came through the Department of Agriculture's research facility in Peoria, Illinois. This might seem an unusual place to solve a medical manufacturing problem, but the Peoria laboratory had developed extensive expertise in fermentation processes, particularly in growing microorganisms in large quantities. They had worked on everything from producing vitamins to finding uses for agricultural surplus. The scientists there understood the practical challenges of cultivating living organisms for commercial production in ways that medical researchers typically did not. Florey and Heatley found themselves in a remarkably different environment from Oxford's ancient stone buildings and genteel academic atmosphere. The Peoria laboratory was practical, industrial in its mindset, and focused on solving production problems. The researchers there listened to Florey's descriptions of growing penicillium in flasks and culture vessels with polite interest, then began asking questions about scaling up, about nutrients that could be used for growth medium, about how to maximize yield. One of the scientists at Peoria, Robert Coghill, immediately grasped the challenge and began working with Heatley on methods to grow the mold more efficiently. They experimented with different nutrient solutions, seeking to find the combination that would produce the most penicillin. Through systematic testing, they discovered that corn steep liquor, a waste product from the process of making cornstarch, worked remarkably well as a growth medium. This was exactly the kind of practical innovation that would make mass production feasible. Corn steep liquor was cheap, abundant, and particularly plentiful in America's agricultural heartland. Meanwhile, Florey traveled to meetings with pharmaceutical companies, presenting the case for penicillin production. These conversations required a different kind of persuasion than scientific lectures. Company executives needed to understand not just that penicillin worked, but that it could be manufactured profitably, that there would be demand for it, and that the investment of resources and facilities would be worthwhile. Florey, more comfortable in laboratories than boardrooms, nevertheless made his case with quiet persistence and the compelling evidence of what penicillin had achieved in the few patients who had received adequate treatment. Several companies expressed interest, seeing both the humanitarian potential and the commercial opportunity. Merck, Squibb, and Pfizer were among those who committed resources to developing production methods. Each brought different expertise and approached the problem from various angles. The American pharmaceutical industry, larger and more developed than Britain's, had the capacity to attempt multiple approaches simultaneously, something that would prove valuable as they discovered which methods worked best. The timing of Florey's visit carried its own significance. When he arrived in July, America was still technically at peace, though providing support to Britain and clearly moving toward involvement in the war. By December, following the attack on Pearl Harbor, the United States entered the conflict fully, and penicillin suddenly became not just a promising medicine, but a military necessity. The meetings Florey had conducted, the relationships he had established, and the groundwork he had laid meant that when the urgency became acute, the infrastructure for response was already beginning to form. Florey returned to England that autumn, leaving Heatley to continue working at Peoria on production methods. The journey had accomplished what he hoped. It had planted penicillin in soil where it could grow beyond the limits of what Oxford could achieve. The American pharmaceutical industry, American scientific expertise in fermentation, and soon American military need would combine to push penicillin production forward with an intensity and scale that the small Oxford laboratory could never have achieved alone. The transatlantic partnership that began with Florey's journey would prove essential to penicillin's story. Britain had made the scientific breakthroughs, but America would master the industrial challenge of production. Together, they would transform a moldy curiosity from a London laboratory into medicine that would reach battlefields and hospitals around the world. The problem that greeted Howard Florey and his colleagues upon their arrival in America was both simple and profound. They had proven that penicillin could save lives. They had demonstrated its remarkable power against bacterial infections, but they could produce only the tiniest quantities, barely enough to treat a handful of patients. What they needed was a way to produce penicillin, not by the thimbleful but by the gallon, by the barrel, eventually by the ton. The traditional method of growing Penicillium mold, the one Fleming had stumbled upon and the Oxford team had refined, involved surface culture. The mold grew on the surface of a liquid medium in shallow containers, producing small amounts of the precious substance over many days. It was painstaking work that required enormous space for modest yields. If you wanted more penicillin, you needed more containers, more laboratory space, more technicians to tend each individual flask. The mathematics were discouraging. To supply even a single military hospital would require warehouses full of growing containers. American researchers approached this challenge with fresh perspectives and industrial ambitions. At the Northern Regional Research Laboratory in Peoria, Illinois, a government facility that had been studying agricultural problems, scientists began exploring whether deep tank fermentation might offer a solution. This technique, already used in other industries, involved growing microorganisms throughout large vats of liquid rather than just on the surface. Imagine the difference between a pond, where life concentrates at the surface and edges, and an aquarium with an aerator, where organisms can thrive throughout the entire volume of water. The concept was appealing, but translating it to penicillin production proved remarkably challenging. The penicillium mold was temperamental. It had evolved to grow on surfaces, not suspended in liquid. The researchers in Peoria had to become both scientists and mold whisperers, learning the particular preferences and peculiarities of this microscopic organism. They experimented with different nutrients, testing everything from simple sugars to complex organic compounds. They adjusted temperatures, controlled oxygen levels, and monitored acidity with meticulous care. One breakthrough came from an unexpected quarter. The Penicillium notatum strain that Fleming had discovered, and that the Oxford team had been using, was not particularly productive. Perhaps there existed other strains of Penicillium that might generate more of the antibiotic substance. The Peoria laboratory launched what might be called a mold collection program, gathering samples from around the world. Soil samples arrived from distant locations. Researchers examined moldy materials of every description, testing each specimen for its penicillin-producing potential. The most famous discovery in this search came from remarkably close to home. A laboratory assistant named Mary Hunt became known around the facility for her dedication to examining moldy produce at the local market. One day in 1943, she brought back a cantaloupe from a Peoria fruit market, its skin covered with a golden mold. When tested, this particular strain of Penicillium chrysogenum produced significantly more penicillin than the strains they had been using. Further work with this Peoria cantaloupe strain, including exposure to ultraviolet light and X-rays to induce mutations, eventually yielded varieties that produced 200 times more penicillin than Fleming's original mold. The fermentation process itself became a marvel of biological engineering. Large steel tanks, some holding thousands of gallons, became the new homes for Penicillium cultivation. These tanks required constant supplies of sterile air, pumped through the liquid to provide oxygen throughout the medium. The mold needed to be fed a carefully balanced diet. Too much of certain nutrients and it would grow abundantly, but produce little penicillin. Too little, and growth would stall entirely. Engineers designed specialized agitators to keep the liquid in gentle motion, preventing the mold from settling, while avoiding the damage that excessive turbulence might cause to the delicate fungal structures. Temperature control became critical on this new scale. While a small flask in a laboratory could be kept at a constant temperature relatively easily, maintaining precise conditions in a 10,000-gallon tank presented engineering challenges. Cooling coils wound through the tanks, carrying away the heat generated by the mold's own metabolism and the mechanical stirring systems. The timing of harvest mattered enormously. Penicillin production followed a particular pattern as the mold culture aged. Extract too early, and you missed the peak of production. Wait too long, and the mold itself would begin breaking down the penicillin molecules. Operators learned to recognize the optimal moment by carefully tracking the culture's progress, measuring penicillin concentrations at regular intervals. Chemical companies brought their own expertise to the process. Merck, Squibb, and Pfizer were among the pharmaceutical firms that invested in this new technology. Their chemists refined the extraction and purification techniques, developing methods to separate penicillin from the complex brew of the fermentation tank. What emerged was still far from pure, but it was concentrated enough to be medically useful and stable enough to be transported and stored. The collaboration between academic researchers, government laboratories, and private industry represented something relatively uncommon in American pharmaceutical development. The wartime emergency had created a shared purpose that transcended normal competitive boundaries. Techniques and findings were shared among the participating organizations. When one company made a breakthrough in fermentation conditions, others could adopt the innovation. When university researchers discovered a better extraction method, the industrial partners implemented it. Production numbers began to climb in a way that would have seemed fantastical just years earlier. From the microgram quantities of the Oxford laboratory, production increased to grams, then kilograms, then hundreds of kilograms. By 1943, American pharmaceutical companies were producing penicillin in quantities sufficient to treat thousands of patients. The Fermentation Revolution had transformed penicillin from a laboratory curiosity into an industrial product. Yet even as production scaled upward, demand seemed always to race ahead. Military planners calculated their needs based on anticipated casualties from the ongoing war. Every wounded soldier who might develop an infection represented a potential need for penicillin. The production lines ran continuously, their precious output carefully allocated according to military priorities. The deep tank fermentation process, refined through countless hours of experimentation and adjustment, had solved the production puzzle. What remained was to scale it further still, to build more tanks, to establish more production facilities, to train more operators in the exacting techniques required to coax maximum yields from these microscopic living factories. The stage was set for an unprecedented expansion of pharmaceutical manufacturing, driven by the desperate necessities of global conflict. By early 1942, the technical breakthroughs in fermentation had opened a door, but walking through it required something altogether different: industrial might, on a scale never before applied to a pharmaceutical product. The knowledge of how to grow penicillin was one thing. Actually producing millions upon millions of units of this fragile molecule was quite another. The American government, now fully committed to war, recognized what penicillin could mean for wounded soldiers. The Office of Scientific Research and Development coordinated efforts, bringing together companies that had traditionally been fierce competitors. In conference rooms and on factory floors, representatives from Merck, Squibb, Pfizer, and others sat side by side, sharing secrets that would normally have been guarded with absolute vigilance. Patent concerns were set aside, proprietary processes were openly discussed. The normal rules of business competition dissolved in the face of wartime necessity. Each company brought different strengths to the challenge. Some had expertise in fermentation technology, from decades of producing chemicals and vitamins. Others understood pharmaceutical-grade purification. Still others specialized in the precise glassware and equipment needed for sterile production. Together, they formed a collaborative network that would have been unimaginable in peacetime. The first obstacle was simple space. Deep tank fermentation required enormous vessels, far larger than anything previously used for pharmaceutical production. Companies began converting existing facilities and building new ones at unprecedented speed. In Brooklyn, Pfizer committed its entire production capacity to penicillin, installing massive fermentation tanks in a building that had produced citric acid. The tanks, each holding thousands of gallons, required careful temperature control, precise aeration, and constant monitoring. Engineers worked around the clock designing pumps, valves, and filtration systems that could handle the delicate biological process. The mold itself remained temperamental, even as strains improved. Temperature fluctuations of just a few degrees could ruin an entire batch. Contamination by other microorganisms spelled disaster. The medium in which the mold grew required exact formulations, and ingredients had to meet exacting standards of purity. Corn steep liquor, that humble byproduct of cornstarch manufacturing, became a strategic material, allocated and tracked with care. Workers in these new penicillin factories learned skills that had never existed before. They became experts in maintaining sterile conditions on an industrial scale, in recognizing the subtle signs that a fermentation batch was progressing properly, in troubleshooting problems with living biological systems rather than straightforward chemical reactions. Women, many of whom had entered the workforce as men departed for military service, operated complex equipment and made critical decisions about production processes. The purification stage presented its own formidable challenges. Penicillin made up only a tiny fraction of the fermentation broth. Separating this precious substance from thousands of gallons of liquid containing proteins, sugars, and countless other molecules required ingenuity and precision. Teams developed multi-stage extraction processes using solvents, carefully controlled pH levels, and filtration through materials that could capture penicillin molecules while allowing impurities to pass. Even as engineers solved one problem, others emerged. The penicillin molecule proved frustratingly unstable. Heat destroyed it. Certain pH levels broke it down. Time itself was an enemy, as penicillin gradually degraded even under supposedly ideal conditions. This meant production had to coordinate precisely with distribution and use. There was no point manufacturing large quantities if they would lose potency before reaching patients. Packaging became a critical concern. Small vials had to be filled under sterile conditions, sealed perfectly, and labeled accurately with potency information. Glass suppliers worked to provide containers that met specifications. Rubber stoppers had to be free from contaminants that might react with penicillin. Every detail of the supply chain demanded attention. Through 1942 and into 1943, production climbed steadily. What had been grams became kilograms, then hundreds of kilograms. Companies invested millions of dollars in facilities that might become obsolete if the war ended suddenly, or if penicillin proved less valuable than hoped. But the clinical results kept coming, each one more encouraging than the last. Patients who would certainly have died survived. Infections that would have meant amputation cleared up completely. The investment seemed not just justified but essential. The government tracked every unit produced. Military needs received priority, with careful allocation to different theaters of war, based on casualty projections and strategic importance. Committees met regularly to review production figures, discuss bottlenecks, and plan expansion. The urgency never diminished. More soldiers were wounded every day, and each one represented a potential life that penicillin might save. By 1943, production had reached levels that would have seemed impossible just 2 years earlier. Yet demand continued to outpace supply. Pharmaceutical companies launched additional expansion projects, building new fermentation facilities and hiring more workers. The knowledge gained from early production runs informed each new facility, allowing improvements in efficiency and yield. Research continued alongside manufactures. Scientists still didn't fully understand penicillin's chemical structure, but they kept investigating, hoping knowledge might lead to even better production methods, or perhaps enable synthetic manufacture. Other researchers screened thousands of mold samples, searching for strains that might produce even more penicillin or grow more reliably. Every incremental improvement mattered when multiplied across millions of liters of fermentation broth. The collaboration extended beyond companies to universities and government laboratories. Information flowed through formal channels and informal networks. A breakthrough at one location would be rapidly communicated to others. Published papers were rushed through review processes. The scientific method continued, but accelerated and focused with laser intensity on a single goal: more penicillin, faster, cheaper, better. By 1944, American pharmaceutical companies were producing penicillin in quantities sufficient not just for military use, but with the prospect of civilian availability on the horizon. The price per dose, which had been astronomical in the early days, dropped steadily as production scaled up and processes improved. What had been a precious substance reserved for the most critical cases was becoming abundant enough to treat more routine infections. This industrial transformation happened in just a few years, a period that would normally represent the planning phase for such complex facilities. The war had compressed timelines and eliminated obstacles that would have delayed progress in peacetime. But more than speed, the collaboration itself represented something remarkable. Competitors working together, sharing knowledge freely, focused on a mission beyond profit. As production facilities hummed day and night, the next challenge was already emerging: getting this precious medicine to the soldiers who needed it, often on distant battlefields, where conditions were anything but ideal for handling a delicate pharmaceutical product. The manufacturing miracle was complete, but the distribution miracle was just beginning. The factories had achieved the impossible, producing penicillin in quantities that would have seemed like fantasy just 2 years earlier. Now came the moment of truth. Would this golden substance, grown in enormous steel tanks and purified through countless intricate steps, actually save lives on the battlefield? The wounded soldiers waiting in field hospitals across multiple theaters of war would provide the answer. In North Africa, where Allied forces fought through desert heat and dust, military doctors received their first shipments of penicillin in late 1943. The timing could not have been more critical. Battlefield wounds in the desert presented unique challenges, with sand and debris driven deep into injuries by the force of explosions and shrapnel. These contaminated wounds regularly became infected, and even with the best surgical care available, many soldiers faced amputations or worse. The medical officers who unpacked those first precious vials of penicillin carried both hope and uncertainty. Laboratory results were one thing, battlefield conditions were quite another. The early cases treated with penicillin in North Africa provided dramatic results that spread quickly through medical channels. Soldiers with infected wounds that would typically require amputation began healing after receiving injections of the new drug. The suppuration that characterized infected injuries started clearing within days. Men who would have spent months recovering, if they recovered at all, were returning to health in weeks. Medical officers documented case after case, carefully recording dosages, treatment duration, and outcomes. The reports flowing back to command headquarters painted a picture that seemed almost too good to be true. As Allied forces pushed into Italy in 1943 and 1944, penicillin moved with them. The Italian campaign, with its difficult terrain and fierce fighting, produced devastating casualties. Field hospitals set up in commandeered buildings, tents and any available shelter received a steady stream of wounded men. The introduction of penicillin into these forward medical facilities transformed what doctors could accomplish. Injuries that previously meant certain evacuation to distant hospitals could now be treated closer to the front lines. The drug proved effective against the multiple bacterial infections that commonly afflicted combat wounds: Staphylococcus, Streptococcus, and the particularly dangerous gas gangrene organism. The dosing schedules developed during this period reflected the drug's rapid elimination from the body. Soldiers received injections every 3 or 4 hours, around the clock. In busy field hospitals, this meant medical staff moving constantly between patients, administering the medication through the night. The drug had to be dissolved and prepared fresh for each injection. Despite these logistical challenges, medical teams maintained the rigorous schedules, knowing that maintaining adequate levels in the bloodstream made the difference between success and failure. Across the English Channel, as D-Day approached, military planners incorporated penicillin into their medical preparations. The anticipated casualties from the invasion of Normandy drove urgent requests for increased production. Pharmaceutical companies pushed their fermentation tanks to maximum capacity. When Allied forces landed on the beaches of Normandy in June 1944, penicillin came with them. Medical units wading ashore carried the drug among their essential supplies, packed carefully to protect it from water and damage. The Normandy campaign validated every hope placed in penicillin. The scale of casualties during and after the invasion overwhelmed medical facilities, yet infection rates remained remarkably lower than military doctors had experienced in previous conflicts. Wounded men received penicillin as soon as they reached aid stations, often within hours of injury. This early intervention proved crucial in preventing infections from taking hold. The drug bought time for surgical teams working frantically to treat the most serious injuries. It allowed medics to stabilize patients for evacuation to better-equipped hospitals in England. In the Pacific Theater, where American forces island-hopped across vast ocean distances, penicillin faced different challenges. The tropical climate created ideal conditions for bacterial growth in wounds. High humidity, heat, and the difficulty of maintaining sterile conditions in jungle environments meant infections developed rapidly and aggressively. The distances between frontline positions and hospital ships or rear area facilities added urgency to effective treatment. Penicillin proved its worth here too, controlling infections in conditions that would have been nearly impossible to manage with previous treatments. The drug's impact extended beyond traumatic battle wounds. Military forces in all theaters struggled with various infections that could disable soldiers without a shot being fired. Pneumonia, which had killed many during World War I, responded well to penicillin treatment. The venereal diseases that historically plagued military populations could now be treated quickly and effectively, returning soldiers to duty rather than requiring prolonged hospitalization. Even minor infections that might have worsened without treatment could be handled efficiently, preserving fighting strength. Medical officers who had served in the First World War found themselves witnessing a transformation they had hardly dared imagine. They remembered the wards filled with men suffering from infected wounds, the smell of gangrene, the difficult decisions about amputation, and the many deaths from infections that began in relatively minor injuries. Now they watched soldiers with similar or worse injuries recover because of a substance derived from a common mold. The contrast between the two conflicts, separated by less than 3 decades, seemed to span a much greater gulf in medical capability. The military medical system gathered extensive data on penicillin's use, creating what amounted to a vast clinical trial under battlefield conditions. Thousands of cases provided information about optimal dosing, treatment duration, which types of infections responded best, and what complications might arise. This practical knowledge, gained under the pressure of wartime necessity, would prove invaluable when penicillin became available for civilian use. The military experience answered questions that might have taken years to resolve through peacetime research. Supply challenges persisted throughout the war. Despite increasing production, military medical units operated under strict allocation systems, reserving penicillin for cases where it would make the most difference. Decisions about which patients would receive the drug involved difficult calculations about severity of injury, likelihood of benefit, and available quantities. As the war progressed and production continued expanding, these rations gradually eased, but penicillin never became abundant enough to lose its status as a precious resource requiring careful stewardship. By the time victory in Europe arrived in May 1945, penicillin had treated hundreds of thousands of Allied servicemen. The drug that began the war existing only in tiny quantities, extracted in Oxford laboratories, had become an integral part of military medicine. Survival rates for wounded soldiers had improved dramatically compared to any previous conflict. The reduction in infection-related deaths and disabilities represented one of the war's unqualified successes, a triumph of science and industrial capacity, working together toward a humanitarian goal. As soldiers began their journeys home, many owed their lives or their intact limbs to the drug that Fleming had noticed on a contaminated culture plate 17 years earlier. The battlefield had proven what penicillin could do. Now attention would turn to bringing this miracle to the civilians who had waited while military needs took priority. While penicillin transformed battlefield medicine in North Africa, Italy, and across the Pacific Theater, back home in American and British cities, the miracle drug remained tantalizingly out of reach for ordinary citizens. The newspapers carried stories of the wonder medicine that could cure infections, once considered death sentences. Yet when a civilian walked into a hospital with pneumonia or a dangerous wound infection, Penicillin was almost certainly unavailable. This created one of the most challenging periods in the drug's early history, a time when knowledge of salvation existed, but access remained restricted to those in uniform. The situation created extraordinary tensions within the medical community. Doctors who read the remarkable reports from military hospitals found themselves helpless when treating civilian patients with identical conditions. A child with bacterial meningitis, a young mother with childbed fever, an elderly man with pneumonia, all might have been saved with penicillin, yet the drug simply did not exist in quantities sufficient for general use. Every vial, every dose went to military channels first. The production lines that had scaled up so dramatically were still inadequate to meet even military needs fully, let alone provide for the home population. The public's awareness of penicillin grew rapidly through 1943 and 1944. Magazine articles appeared with increasing frequency, describing the dramatic rescues on battlefields and in field hospitals. Life magazine published photographs of the fermentation tanks where the precious mold grew. Radio programs featured interviews with doctors who had witnessed penicillin's effects. The drug captured the popular imagination in a way few medical discoveries had before. Here was something tangible, something that represented hope and scientific progress during a time of tremendous anxiety and loss. This widespread knowledge without access created painful situations. Letters poured into pharmaceutical companies, government offices, and research laboratories from desperate families. Parents of sick children begged for even a small amount of the drug. Doctors wrote impassioned pleas on behalf of dying patients. Some letters offered substantial sums of money, life savings, anything for a chance at treatment. These requests revealed both the public's faith in penicillin and the agonizing reality that wartime priorities left civilian medicine operating much as it had before Fleming's discovery. A few civilian cases did receive penicillin treatment during this period, though through exceptional circumstances rather than regular medical channels. The process for obtaining the drug involved layers of approval and justification. A doctor would need to contact the pharmaceutical company, explain why the case was desperate enough to warrant precious supplies, and await a decision. Sometimes approval came through connections, sometimes through the unusual nature of a case that might provide useful medical information, sometimes through sheer persistence and luck. One of the most publicized early civilian cases involved a young girl with bacterial endocarditis, an infection of the heart that was almost invariably fatal. Her physician managed to obtain enough penicillin for a treatment course, and the child recovered. The newspapers celebrated this victory, but the story also highlighted the impossible position of doctors who had other patients equally desperate but no access to treatment. For every case that received penicillin, hundreds of similar cases went untreated. The ethical dimensions of rationing became increasingly complex as production slowly increased but remained insufficient. Who should receive penicillin when not everyone could? Military personnel certainly had priority. But within civilian medicine, how should decisions be made? The young versus the old? Those with the best chance of recovery? Those whose survival served some greater purpose? These questions had no comfortable answers, and different institutions developed different approaches, all unsatisfying in their own ways. Some black markets emerged, small and largely ineffective given the extreme scarcity, but their existence troubled officials. The idea that access to life-saving medicine might depend on wealth or connections rather than medical need contradicted deeply held values about healthcare. Yet the shortage made some degree of unfairness almost inevitable. Well-connected families sometimes obtained treatment that others could not, though the overall supply remained so limited that even privilege offered no guarantee. Medical researchers continued to work with the small quantities available for civilian use, carefully documenting each case, learning more about the drug's capabilities and limitations. These studies explored different bacterial infections, different dosing schedules, different patient populations. Each treated patient contributed information that would eventually help guide wider use. The researchers walked a difficult line between scientific investigation and the immediate human need before them, trying to advance knowledge while conscious that their supplies might save lives if distributed differently. The pharmaceutical companies pushed production as rapidly as possible, but the process remained complex and demanding. Each batch required careful monitoring, specific environmental conditions, and extensive testing. The yields improved steadily as techniques refined, yet the enormous demand meant supplies remained tight throughout 1943 and into 1944. Workers in the fermentation plants understood that their labor directly impacted survival on the battlefield, which provided motivation during long shifts and challenging conditions. Public health officials prepared for the eventual civilian release, knowing that when it came, the transition would need careful management. Educational programs would be necessary to help doctors use the drug effectively, as military experience had revealed both the remarkable potential and the specific limitations of penicillin. Not all bacterial infections responded equally well, and some strains showed more resistance than others. Proper dosing mattered enormously, as the early case of the Policeman in Oxford had so tragically demonstrated when supplies ran out mid-treatment. The waiting period, difficult as it was, served a purpose beyond simply accumulating production capacity. The military use provided an enormous practical trial, teaching lessons about administration, dosing, side effects, and effectiveness against various infections. This knowledge would prove invaluable when civilian distribution began. The wartime experience, purchased at the cost of delayed civilian access, created a foundation of practical wisdom that would help maximize penicillin's benefit when it finally reached general medicine. By late 1944, as production continued its steady climb and military needs began to be met more reliably, the possibility of civilian availability moved from distant hope to near-term reality. The conversations shifted from whether penicillin would reach the public to when and how. The home front had waited through years of promise unfulfilled, watching the miracle drug work wonders in distant theaters of war while remaining unavailable at the local hospital. That long anticipation was finally approaching its end, and with it would come a transformation of everyday medicine, as profound as anything that had occurred on the battlefield. The war in Europe ended in May 1945, and 3 months later, the Pacific conflict concluded as well. After years of rationing, sacrifice, and uncertainty, peace had finally arrived. Among the countless changes that peacetime would bring, one transformation would touch nearly every household in America and Britain. Penicillin, that remarkable substance that had saved so many soldiers on distant battlefields, was finally coming home. Throughout the war years, civilians had read newspaper stories about the miracle drug. They had heard whispered accounts from neighbors whose sons or brothers had survived terrible wounds thanks to penicillin. Mothers had written letters to pharmaceutical companies and government officials, pleading for access to the medicine that might save a dying child. The standard reply had been apologetic but firm. Every available unit of penicillin was needed for military purposes. The home front would have to wait, but now, with the guns silent and factories no longer producing tanks and bombers, that situation could finally change. The massive fermentation facilities that had been constructed to supply military needs still stood ready. The pharmaceutical companies that had learned to produce penicillin by the billions of units possessed both the knowledge and the equipment. The question was no longer whether penicillin could be made in sufficient quantities, but rather how quickly it could be distributed to the doctors and hospitals that had waited so long. The transition happened with remarkable speed. By late 1945, penicillin began appearing in civilian pharmacies and hospital formularies. Doctors who had spent years treating infections with hot compresses, sulfur drugs, and hope could now reach for a medicine that worked with astonishing effectiveness against a wide range of bacterial diseases. The drug that had once been so precious that patients' urine was collected and processed to recover excreted penicillin for reuse now came in small glass vials, available for ordinary medical practice. For physicians who had practiced medicine in the years before antibiotics, the change felt almost miraculous. A family doctor making house calls in a small Midwestern town could now treat a child's strep throat infection with confidence rather than worry. A surgeon in a city hospital could perform operations that would have been unthinkably risky just a few years earlier, knowing that bacterial infections could be controlled. The pneumonia that had filled wards with struggling patients and anxious families became a treatable condition rather than a potential death sentence. The public's response to penicillin's availability mixed relief with tremendous enthusiasm. Newspapers ran stories about children saved from ear infections that might have led to dangerous complications. Magazines published articles explaining how the mold-derived medicine worked, often illustrated with photographs of the penicillium cultures that produced the life-saving substance. Penicillin became not just a medicine but a symbol of scientific progress and hope for the future. Pharmaceutical companies, recognizing both the medical need and the commercial opportunity, ramped up production even further. The manufacturing techniques that had been developed under wartime urgency continued to be refined and improved. New fermentation facilities were constructed. Competition among drug makers drove innovation and helped push prices downward, making the treatment more accessible to hospitals and patients of modest means. The impact on everyday medical practice proved profound. Conditions that had filled hospital beds for weeks could now be treated in days. Infections that had required long convalescences often resolved with a course of penicillin injections. The childhood diseases that had worried every parent, scarlet fever, rheumatic fever complications, severe ear infections, became far less frightening. Life insurance companies began revising their actuarial tables as mortality rates from infectious diseases dropped. In maternity wards, the change was especially dramatic. Childbed fever, that ancient scourge that had killed countless new mothers, could now be treated effectively when it occurred. The puerperal infections that had made childbirth dangerous even in modern hospitals became manageable complications rather than potential tragedies. Young mothers went home to their families instead of being lost to infections that started in the hours after delivery. The medical profession adapted to this new reality with a mixture of gratitude and adjustment. Older physicians, who had trained in an era when bacterial infections were treated with limited options, found themselves learning new protocols and dosing schedules. Younger doctors, completing their training in the late 1940s, entered a medical landscape transformed from the one their professors had known as students. Medical schools updated their curricula to include antibiotic therapy as a fundamental tool, yet this transition was not without its complications. As penicillin became widely available, questions arose about appropriate use. Some physicians prescribed it enthusiastically for almost any infection, while others urged restraint and careful diagnosis. The drug worked magnificently against certain bacteria, but had no effect on viral infections or other types of microorganisms. Learning which conditions would respond to penicillin and which would not became an important part of medical practice. Stories began to circulate about allergic reactions to penicillin, a reminder that even miracle drugs came with risks. Some patients developed rashes or more serious immune responses. The medical community learned to ask about previous reactions and to monitor patients during treatment. These complications were rare compared to penicillin's benefits, but they added nuance to the initial enthusiasm. By 1946 and 1947, penicillin had become an established part of medical practice across America and Britain. The sight of those small vials in doctors' offices and hospital pharmacies represented a quiet revolution in human health. Parents could watch their children recover from infections that might have proved fatal a decade earlier. Surgical patients could undergo procedures with dramatically reduced risk of post-operative infection. The elderly could survive pneumonias that would previously have been their final illness. The pharmaceutical industry, having proven it could meet the wartime challenge, now faced the equally important task of sustaining production for peacetime needs. The collaboration between companies that had developed during the war continued, with manufacturers sharing improvements and innovations. The price of penicillin continued to fall as production methods became more efficient, making the treatment accessible to an ever wider population. As 1948 approached, penicillin had completed its journey from laboratory curiosity to military secret to household word, the medicine that Alexander Fleming had stumbled upon in a contaminated petri dish that Florey and Chain had painstakingly purified in their Oxford laboratory, and that American industry had learned to produce by the ton, was now saving lives in small towns and large cities across the developed world. The antibiotic age had truly begun, and medicine would never be the same. Yet even as penicillin transformed treatment of bacterial infections, researchers were already searching for the next generation of antimicrobial drugs, building on the foundation that had been laid. As penicillin transformed from miracle drug to everyday medicine in the years following the war, something remarkable was happening in laboratories around the world. Scientists had learned an invaluable lesson from Fleming's fortunate accident and the triumphant success that followed. If one mold could produce such a powerful substance against bacteria, perhaps nature held other secrets waiting to be discovered. The search was on, and this time it would be deliberate, systematic, and urgent. The success of penicillin had illuminated a path forward. Researchers now understood that microorganisms themselves might be weapons against disease, that the microscopic world contained its own competitions and chemical defenses. Where Fleming had stumbled upon his discovery, scientists now began to search with purpose, collecting soil samples from every corner of the earth, examining countless microorganisms for antibiotic properties. The pharmaceutical companies that had mastered penicillin production turned their attention and resources to finding the next wonder drug. One of the most important discoveries came from an unlikely source. Selman Waxman, a soil microbiologist at Rutgers University in New Jersey, had spent decades studying the organisms living in earth and compost. He understood the complex chemical warfare that occurred invisibly beneath our feet, where countless species of bacteria and fungi competed for resources. Waxman coined the very term antibiotic to describe these substances that one microorganism produces to inhibit another. His systematic approach to screening soil microorganisms would prove extraordinarily fruitful. In 1943, one of Waxman's graduate students, Albert Schatz, isolated a bacterium from a heavily manured field and from the throat of a healthy chicken. This organism, belonging to a group called Actinomycetes, produced a substance that Waxman and Schatz called streptomycin. What made streptomycin particularly significant was its effectiveness against bacteria that penicillin could not touch. Most notably, it proved active against the bacterium that caused tuberculosis, the ancient disease that had claimed countless lives throughout human history. The discovery of streptomycin opened new possibilities in medicine. Tuberculosis patients, who previously faced only rest cures in sanatoriums with uncertain outcomes, now had a genuine treatment, though the story of streptomycin would later be complicated by disputes over credit for its discovery. Its impact on human health was undeniable. Waxman received the Nobel Prize in 1952, though questions about Schatz's contribution persisted for years afterward. Other researchers pursued different approaches. Benjamin Duggar, a botanist working for Lederle Laboratories, examined thousands of soil samples even though he was already in his 70s. In 1945, from a sample collected from a farm in Missouri, he isolated a golden-colored bacterium that produced a substance he called aureomycin, later known as chlortetracycline. This became the first of the tetracycline antibiotics, a family that would prove effective against a remarkably broad range of bacteria. The tetracyclines possessed a quality that made them particularly valuable. They worked against many types of bacteria, earning them the designation broad-spectrum antibiotics. While penicillin was highly effective against certain bacteria and streptomycin against others, tetracyclines could treat a wide variety of infections. This made them especially useful when doctors needed to begin treatment before identifying the exact bacterium causing an illness. Through the late 1940s and into the 50s, the discoveries continued. Chloramphenicol emerged from soil samples collected in Venezuela. Erythromycin was isolated from a soil organism found in the Philippines. Each new antibiotic expanded the physician's ability to treat infections, and each had particular strengths against specific types of bacteria. Some worked where others failed. Some could be taken by mouth while others required injection. Some were better tolerated by patients sensitive to penicillin. The pharmaceutical industry grew rapidly during this golden age of antibiotic discovery. Companies established extensive screening programs, testing thousands upon thousands of soil samples and microorganisms. Researchers developed increasingly sophisticated methods for detecting antibiotic activity, purifying active substances, and testing them for safety and effectiveness. The process became almost industrial in scale, yet still depended on the fundamental insight that nature had already developed powerful antimicrobial chemicals through millions of years of evolution. Medical practice transformed as doctors gained this expanding arsenal of treatments. Infections that had recently been serious or even fatal became routine to treat. Pneumonia, once a leading cause of death, became manageable in most cases. Urinary tract infections, skin infections, and wound infections that might previously have led to severe complications now responded to relatively simple courses of treatment. Surgery became safer still, as surgeons could both prevent and treat infections more effectively. The speed of these discoveries was breathtaking. In little more than a decade, medicine had progressed from having essentially one antibiotic to possessing multiple classes of these drugs, each with different properties and uses. The change represented a fundamental shift in humanity's relationship with bacterial disease. For the first time in history, doctors possessed truly effective weapons against these invisible enemies that had plagued humanity since the beginning. Yet even as researchers celebrated each new discovery, thoughtful observers noticed something concerning. Some bacteria were showing signs of resistance to antibiotics, developing ways to survive exposure to these once deadly substances. Alexander Fleming himself had warned about this possibility in his Nobel Prize speech in 1945. The very success of antibiotics, and perhaps their overuse, would eventually present new challenges. But in these heady years of discovery and hope, when each month seemed to bring news of another miraculous substance, such concerns remained mostly at the margins of attention. The antibiotic family had grown from a single fortunate accident into a robust collection of medicines, each discovered through dedicated searching, careful testing, and the generous secrets that nature revealed when asked the right questions. The transformation of medicine was complete, and the world would never be quite the same. As the war drew to a close and penicillin's remarkable success became undeniable, the scientific world turned its attention to honoring those who had made this miracle possible. The Nobel Committee in Stockholm had watched the penicillin story unfold with great interest, observing as a chance laboratory observation had transformed into one of the most significant medical advances in human history. In the autumn of 1945, just months after the end of World War II, the announcement came that would forever link three names in the annals of medical science. Alexander Fleming, Howard Florey, and Ernst Boris Chain would share the Nobel Prize in Physiology or Medicine. The citation recognized their roles in the discovery and development of penicillin and its curative effect in various infectious diseases. It was a moment that acknowledged not just a single eureka discovery, but the entire chain of scientific progress from observation to practical application. The committee had wisely chosen to honor both the initial discovery and the essential work that had transformed it into actual medicine. The three men received the news in characteristically different ways, reflecting their distinct personalities that had each contributed uniquely to penicillin's journey. Fleming, now famous beyond any scientist's usual measure, accepted the honor with his typical modesty, though he had grown somewhat more comfortable with public attention. Florey, ever the pragmatist, viewed the prize as recognition of his team's methodical work rather than personal glory. Chain, the most emotionally expressive of the trio, felt deeply vindicated for the years of painstaking biochemical work that had made purification possible. The award ceremony in Stockholm that December was a subdued affair, held in a world still recovering from war. The three laureates traveled to Sweden, where they delivered their Nobel lectures to an audience acutely aware of how many lives penicillin had already saved. Fleming spoke of the accidental nature of his discovery and the importance of recognizing the unexpected when it appears. Florey discussed the systematic approach required to transform a laboratory curiosity into practical therapy. Chain detailed the complex chemistry behind isolating and understanding penicillin's molecular structure. What made this particular Nobel Prize remarkable was how it represented genuine international collaboration, even as it honored individual achievement. Fleming's Scottish persistence, combined with the Oxford team's diverse talents, including Chain's German-Jewish heritage and background in biochemistry, showed science transcending national boundaries. The work had ultimately required American industrial might to reach its full potential, creating a truly transatlantic success story. After Stockholm, the three men's paths diverged in ways that reflected their different priorities and temperaments. Fleming became perhaps the most famous scientist of his era, traveling extensively to receive honors and speak about penicillin. He visited countries across Europe, Asia, and the Americas, greeted everywhere as the man who had conquered infection. His lectures drew enormous crowds, and he used his platform to encourage young people to pursue science. Despite the constant attention, he remained at St. Mary's Hospital, continuing his work in bacteriology, though nothing would ever match the impact of that contaminated Petri dish from 1928. Florey returned to his administrative and research duties at Oxford, deliberately avoiding the spotlight that so readily found Fleming. He continued to lead important medical research, serving as president of the Royal Society and later becoming provost of Queen's College, Oxford. His contributions to penicillin's development had been absolutely essential, yet he remained relatively unknown to the general public, which suited him perfectly well. Those who worked with him recognized his organizational genius and his ability to drive complex projects to completion against considerable odds. Chain's post-war career took him in yet another direction. After tensions with Florey over patent issues and credit for their work, Chain eventually left Oxford. He spent time in Rome, establishing a biochemistry research centre, before returning to England as professor at Imperial College London. He continued working on antibiotics and enzymes, maintaining his passionate interest in the chemistry of natural substances. Throughout his life, he remained outspoken about the importance of proper funding for basic research and fair recognition for scientific achievement. The broader legacy of their work extended far beyond personal accolades. The penicillin story had demonstrated conclusively that natural substances could provide powerful medicines, spurring the search for other antibiotics that would continue for decades. It had shown how academic research could partner with industry to solve pressing medical problems. Perhaps most importantly, it had proven that infectious disease need not be humanity's inevitable companion. Medical schools and research institutions around the world drew lessons from the penicillin experience. Universities strengthened their connections with pharmaceutical companies. Governments began investing more substantially in medical research, recognizing it as essential infrastructure rather than mere curiosity. The field of pharmacology expanded dramatically as researchers sought to understand how drugs worked at the molecular level. Microbiology departments grew as scientists explored the complex relationships between microorganisms and human health. Fleming received a knighthood, becoming Sir Alexander Fleming, and continued to warn audiences about the dangers of antibiotic misuse, prescient concerns that would prove increasingly relevant. Florey also received a knighthood, and later became Baron Florey of Adelaide and Marston, one of the rare scientists elevated to the peerage. Chain was knighted as well, becoming Sir Ernst Boris Chain. These honours reflected Britain's recognition of contributions that had enhanced the nation's prestige and humanity's well-being. As the years passed, each man saw penicillin's impact grow in ways they could hardly have imagined during those early experiments. The number of lives saved climbed into the millions, then tens of millions. Diseases that had terrorized previous generations became routinely treatable. Surgeons could perform increasingly complex operations, confident that post-operative infections could be controlled. Mothers survived childbed fever. Children recovered from ear infections and scarlet fever that might once have killed them. The three Nobel laureates maintained varying degrees of contact with each other in their later years. The relationship between Florey and Chain remained somewhat strained, a reminder that scientific collaboration, however productive, involves human personalities with all their complexities. Fleming maintained cordial relations with both, serving as the public face of a discovery that had required all three men's contributions in different measures and at different times. When each man eventually passed away, Fleming in 1955, Florey in 1968, and Chain in 1979, they left behind more than scientific papers and patents. They had demonstrated how observation, persistence, and systematic development could combine to transform human existence. Their story would be told and retold, inspiring countless future scientists to pursue seemingly impractical research, to pay attention to unexpected results, and to persevere through years of difficulty toward distant goals. The years following the Second World War witnessed something unprecedented in human history. For the first time in our existence as a species, common bacterial infections no longer carried the weight of potential tragedy. The transformation happened so quickly that within a single generation, the experience of illness changed fundamentally. Parents who had grown up fearing scarlet fever watched their own children recover from similar infections in a matter of days. The shadow of sepsis that had darkened hospitals and homes began to lift. Life expectancy, which had remained relatively stagnant for centuries despite improvements in sanitation and nutrition, began climbing at a remarkable pace in developed nations. Much of this increase came not from preventing illness, but from successfully treating infections that once proved fatal. A cut sustained while gardening, a bout of pneumonia, an infected tooth. These ordinary mishaps of living no longer held the same menacing potential. The relief rippled through society in ways both obvious and subtle. Surgery transformed from a desperate last resort into a planned medical intervention. Surgeons could now operate with confidence that post-operative infections, once nearly inevitable, could be controlled. This opened possibilities that had existed only in theory. Heart surgery, organ transplants, joint replacements. These advances became feasible because antibiotics stood guard against the bacterial invaders that had previously made such procedures too dangerous to attempt. The operating theater, once a place of grave risk, became a space of possibility. Childbirth became measurably safer. The puerperal fever that had claimed so many new mothers, including Mary Wollstonecraft after giving birth to her daughter, who would write Frankenstein, retreated before penicillin and its sister compounds. Maternity wards that had seen tragedy, despite the best efforts of careful practitioners, found their outcomes improving dramatically. The joy of new life was less frequently shadowed by maternal death. Children, always most vulnerable to the diseases that swept through communities, benefited perhaps most profoundly. Ear infections, once a potential path to deafness or worse, became minor inconveniences. Strep throat, scarlet fever, and the various bacterial illnesses of childhood transitioned from feared killers to manageable conditions. Pediatric medicine entered an age of optimism. The pharmaceutical industry expanded dramatically in the wake of penicillin's success. The race to discover new antibiotics intensified as companies and research institutions recognized both the humanitarian value and commercial potential of these substances. Soil samples from around the world arrived at laboratories for testing. Researchers examined fungi, bacteria, and other organisms, searching for the next compound that might prove useful against infection. The methodical screening of thousands of samples became standard practice, and the efforts yielded results. Streptomycin, chloramphenicol, tetracyclines, and many others joined the medical arsenal. Each new antibiotic brought its own story, its own particular strengths against specific infections. Some worked where penicillin failed. Others reached parts of the body that penicillin couldn't penetrate effectively. Together, they formed a comprehensive toolkit that gave physicians options where once they had only hope and supportive care. The developing world watched these advances with understandable longing. While antibiotics became routine in wealthy nations, access remained limited in many parts of the globe. International health organizations worked to bridge this gap, recognizing that infections respected no borders. Gradually, though unevenly, the reach of antibiotics expanded. Tuberculosis programs brought streptomycin to communities that had seen generations ravaged by the disease. Tropical diseases that had persisted for centuries found themselves confronted with new treatments. The generation of scientists who had struggled to extract tiny quantities of penicillin from moldy cantaloupe rinds lived to see industrial facilities producing tons of antibiotics annually. Fleming, Florey, and Chain witnessed a transformation that exceeded even their hopeful projections. Their discovery had catalyzed changes that touched virtually every aspect of medicine and rippled outward into society itself. Yet the story of antibiotics also carried lessons about the relationship between humans and the microbial world. Bacteria, with their rapid reproduction and genetic adaptability, began developing resistance to the drugs designed to kill them. This wasn't unexpected. Evolution operates continuously, but it served as a reminder that antibiotics were powerful tools requiring thoughtful use. The question of how to preserve the effectiveness of these medicines while ensuring access to those who needed them would continue to challenge medical science. The antibiotic revolution demonstrated what becomes possible when curiosity meets persistence, when international collaboration overcomes national boundaries, and when scientific discovery receives the resources needed to reach practical application. Fleming's fortunate observation mattered little until Florey and Chain committed to the difficult work of purification. Their laboratory success remained limited in impact until the industrial capacity of multiple nations combined to enable mass production. No single step in the journey was sufficient alone. Each phase required the next to achieve the ultimate transformation. Looking back across the decades, the impact appears almost impossible to fully measure. How many lives were saved? How many children grew to adulthood who would have perished? How many medical advances became possible only because antibiotics made them safe? The numbers stretch beyond easy calculation, reaching into the hundreds of millions, perhaps billions, when accounting for subsequent generations born because their parents survived infections. The story of antibiotics reminds us that progress often arrives through unexpected pathways: a vacation taken, a window left open, a laboratory plate not immediately discarded. These small moments connected across time to reshape human existence. It demonstrates the value of supporting scientific curiosity, even when immediate applications seem distant. It illustrates how crises, even the terrible crisis of war, can accelerate beneficial change when directed toward healing rather than harm alone. As we settle into sleep, reflecting on this remarkable journey from Fleming's contaminated culture plate to the transformed medical landscape of the modern world, we might consider how much we benefit from discoveries made by people we'll never meet. Their careful work, their persistence through setbacks, their willingness to share findings across borders and between institutions, created tools that protect us still. The antibiotic age stands as testament to human ingenuity and cooperation, a chapter in our species' story worth remembering as we drift peacefully toward rest. As we bring to a close our journey through the remarkable story of antibiotics, from Fleming's chance observation of a mold to the heroic efforts that brought penicillin to millions, we hope these quiet tales of discovery have gently carried you toward rest. Thank you for joining us on this peaceful exploration of how tiny molecules change the world forever. If these calm adventures have brought you comfort, we'd love to have you with us again. Please like, subscribe, and share your thoughts in the comments below. And now, as the night deepens and your mind settles into stillness, we wish you the sweetest of dreams. Good night, fellow dreamer, and may your sleep be restful and your dreams be kind.